Ever look up at the night sky and feel like you're staring into infinity? That's exactly what you're doing. But here's what most people don't realize. Everything you see up there isn't just randomly scattered chaos. The universe has structure, actual, intricate, mind-bending structure. And the patterns are so enormous and so precise that they make your brain kind of hurt when you actually sit with the idea. Not the abstract hurt of thinking about infinity, but the specific, concrete hurt of trying to understand how organized everything is when you would have expected it to be random, when you would have expected pure cosmic chaos. I remember being like 15, lying in my backyard on one of those nights where you can actually see the Milky Way because the light pollution isn't completely choking it out. You know those nights? Where you look up and you can actually see the band of light across the sky, the actual visible part of our galaxy stretched from horizon to horizon. Those are rare in modern times because of light pollution from cities. Most people have never seen the Milky Way clearly. Most people live under skies so bright from artificial light that the stars are just little points scattered randomly. But on those rare dark nights, you can really see it. You can see the structure of our galaxy. You can see that it's not random. It has shape. It has patterns. I was thinking about how vast space is, right? Like, really thinking about it, trying to comprehend the sheer distance between stars, between galaxies, between galaxy clusters, trying to wrap my mind around what a light year actually means. And my dad comes out. He's an engineer, very practical guy, doesn't really get into science fiction or deep philosophical discussions about the cosmos. He's not the type to ponder the meaning of existence. But he says, you know, the universe is probably built like everything else we design. There's got to be some organizing principle. Architects don't build randomly. Construction follows plans. Nature probably doesn't either. There's probably structure to it. And I was like, Dad, it's space. It doesn't work that way. It's just chaos out there. It's just empty void with stuff scattered everywhere randomly. But he was kind of right. And that totally changed how I thought about cosmology. It opened my mind to the idea that maybe the universe isn't chaos. Maybe there's organization. Maybe there's something deeper going on that my eyes can't see but my brain can understand. What we've discovered over the last few decades, and I mean really discovered, with radio telescopes and space missions and mathematical models running on supercomputers, is that the universe isn't a soup of stars and galaxies just floating wherever. It's organized. It has neighborhoods. It has highways of galaxies connect its clusters. It has walls and filaments of matter and vast voids that stretch for billions of light years. And the way these cosmic structures form and persist is one of the most spectacular physics stories out there. One that involves invisible matter we can't see, gravity playing chess at scales we can barely comprehend, mathematics that describes everything from atoms to existence itself, and patterns that repeat at scales that'd make a mathematician weep. Seriously weep. I've seen cosmologists describe structure formation, and they sound almost spiritual about it, almost reverent, because it's so beautiful and so perfect, and it all emerges from such simple rules. But before we get into the really wild stuff about the cosmic web and dark matter and the philosophy of it all, we need to understand how astronomers even figured this out. How do we know the universe is structured? What techniques did they use? And which brings us to the question, what makes something real when we can't see it? How do we measure the invisible? Let's start with how astronomers figure out how far away things are. This is actually incredibly clever, and it's the foundation for everything we know about cosmic structure. For nearby stars, astronomers use something called parallax. Imagine you hold your finger up and look at it with one eye closed, then the other. Your finger appears to shift position, right? That's parallax. Astronomers do the same thing with stars. They measure the position of a star from Earth, then measure it again 6 months later when Earth is on the opposite side of its orbit around the Sun. The star will appear to shift, position slightly in the background. By measuring that shift and knowing the distance Earth travels in 6 months, which is 2 times the Earth-Sun distance, about 300 million kilometers, astronomers can triangulate how far away the star is using basic trigonometry. It's the same principle surveyors use to measure distances on Earth. This works for relatively nearby stars, up to a few thousand light years away. But beyond that, the shifts become too small to measure accurately with current technology, even with space telescopes. Which means we need other techniques for more distant galaxies. For distant galaxies, astronomers use something called standard candles. If you know how bright something actually is, its intrinsic luminosity, and you measure how bright it appears from Earth, you can calculate how far away it is. It's like seeing a light bulb in the distance. If you know it's a 60-watt bulb, you can figure out how far away it is based on how dim it looks. The relationship follows an inverse square law. If you double the distance, the light appears 4 times dimmer. Astronomers use supernovae as standard candles because certain types, particularly type 1a supernovae, have relatively consistent brightness. They also use Cepheid variables, stars that pulse with regular brightness variations. By measuring the period of pulsation, astronomers can determine the star's intrinsic brightness. Then they can measure how bright it appears and calculate distance. This technique was actually how Edwin Hubble first proved that Andromeda was a separate galaxy outside the Milky Way in 1924. He measured Cepheid variables in Andromeda and calculated that it was way farther away than anyone thought. That discovery revolutionized cosmology. But there's another technique that's absolutely crucial for measuring distances to incredibly distant galaxies: the Doppler effect. When something moves toward you, the light it emits gets compressed, the wavelengths get shorter, the light shifts toward blue. When something moves away, the light gets stretched, the wavelengths get longer, the light shifts toward red. By measuring this redshift, how much the light is shifted toward red, astronomers can determine how fast something is moving away from us. And thanks to Hubble's discovery that the universe is expanding, the faster something is moving away, the farther away it is. There's a simple relationship. Velocity equals the Hubble constant times distance. This lets astronomers measure distances to incredibly distant galaxies, billions of light years away. This is how we've mapped the cosmic web. This is how we know the structure of the universe. So armed with these measurement techniques, parallax, standard candles, and redshift measurements, astronomers discovered something shocking in the 20th century. Galaxies aren't randomly distributed. They're organized, they're clustered, there's structure. And the deeper they looked, the more structure they found. Which brings us back to stars and galaxies. Let's start small, and I mean small relative to the universe, but not small in any absolute sense. A star is genuinely massive. The Sun, our star, is about 109 times wider than Earth. You could fit 1,000,000 Earths inside the Sun. 1,000,000. Line them up one after another inside the Sun's volume, and you'd fill it completely. The Sun's diameter is about 1.4 million kilometers. Earth's diameter is about 12,700 kilometers. Do the math. The Sun contains 1,000,000 Earths, and here's the crazy part. The Sun is a medium-sized star. Nothing special. Average. Totally ordinary in galactic terms. There are red giants that are thousands of times bigger than the Sun. Betelgeuse, for instance, is so large that if you put it where the Sun is, its surface would extend past the orbit of Mars. There are even larger stars, hypergiants, that would make Betelgeuse look tiny. UY Scuti is one of the largest known stars, with a radius about 1,700 times bigger than the Sun. If you put UY Scuti where the Sun is, Mercury, Venus, Earth, and Mars would all be inside the star. When we talk about a star, we're talking about a massive ball of fusing hydrogen and heavier elements, held together by its own gravity, so hot at the core that nuclear fusion is happening constantly, releasing the energy that makes it shine. The Sun has been fusing hydrogen into helium for about 4.6 billion years, and still has about 5 billion years left in it before it becomes a MISO red giant and engulfs the inner planets. But relative to the cosmic structures we're going to talk about, stars are just the fundamental building block. They're the atoms of galaxies, in a way. They're the smallest unit that matters when we're talking about large-scale structure. Stars hang out together in galaxies, held together by gravity. And that's where cosmic structure really gets interesting. Which means a new loop is opening. We're about to zoom out and see bigger structures, and the organization becomes even more apparent. A galaxy is basically a gravitationally bound collection of billions or trillions of stars, plus vast clouds of gas and dust, plus dark matter, which we'll get deep into, all orbiting around a common center. The whole thing is held together by gravity and dark matter. Dark matter dominates the mass budget of galaxies, providing most of the gravitational pull that holds the stars in their orbits. Weird, right? We can't see it, but it's what actually holds everything together. They're swirling in this cosmic dance that's been going on for billions of years. Stars orbit around the galactic center. The whole galaxy rotates. Stars are born from gas clouds. Stars die and go supernova. Planets form around stars. Life might arise on planets. And it's all happening against this backdrop of cosmic structure and gravity. The Milky Way. Our galaxy. The one you live in. The one that contains every star you can see with your naked eye, except for Andromeda, which is a nearby galaxy, has somewhere between 100 billion and 2 trillion stars. And I'm not being hyperbolic when I say scientists literally can't agree on the exact number, because counting is hard when your census area is 100,000 light years across, and when most of the mass of the galaxy is invisible, dark matter that you can't directly observe. We have to estimate based on the visible light we see and extrapolate. We use models and simulations to guess how many stars there are, and different methods give different answers. Some estimates say 100 billion, some say 1 trillion, some say 2 trillion. That's a factor of 20 difference. That's the insane part. We don't even know if we're off by a factor of 10. We live in a galaxy. We've been studying it for centuries with naked eyes. We've built massive telescopes. We've sent space missions. We've done surveys that mapped millions of stars. We've used infrared telescopes to look through the dust. And we still can't agree on how many stars are in it. It's humbling. It's also kind of hilarious in a cosmic way. Let me put that in perspective because the math is genuinely mind-breaking, and I want you to really feel how impossible these numbers are. If the Milky Way has 2 trillion stars, the high estimate, and you spent your entire life counting stars, like non-stop, no sleep, no food, no water, no breaks, just counting one star after another, and you could somehow count one star per second without getting confused or losing track or your brain melting from boredom, it would take you 63 million years to count them all. 63 million years, that's an incomprehensibly long time. Humans have only been around for about 300,000 years as a species. Our entire species' existence, from our earliest ancestors to now, is about 0.5% of the time it would take to count all the stars in one galaxy. Let that sink in. Think about that for a moment. Everything humans have ever done, all of recorded history, all of civilization, all of art and science and love and conflict and revolution and discovery, has happened in about 0.5% of the time it would take to count the stars in our galaxy. We're tiny. We're insignificant in time. But we're here. We're conscious. We're aware. We can understand this. And that's just one galaxy. There are more galaxies in the observable universe than there are stars in the Milky Way. We're talking about 2 trillion galaxies at last count, though we keep revising that number upward as our telescopes get better, and we can see further back in time. So you've got 2 trillion galaxies, each with potentially hundreds of billions or trillions of stars. You've got 10 to the 24th power stars, or maybe even more. The numbers are so large they stop meaning anything to the human brain. The human brain evolved to think about dozens, maybe hundreds of things. We can barely conceptualize millions. Billions is stretching it. Trillions is beyond our grasp, and we're talking about numbers that make trillions look small. The scale is incomprehensible. Our brains didn't evolve to handle these numbers. Our galaxy, the Milky Way, is what we call a spiral galaxy. It's got these elegant sweeping arms that make it look like someone smeared a whirlpool across the cosmos. It's beautiful. It's the kind of thing that makes you feel small and wonder about your place in the universe. If you've ever seen a photo of a galaxy from above, and you definitely have if you've scrolled social media literally at all, astronomy photos are everywhere on Instagram and Reddit. That's probably a spiral galaxy. The Andromeda Galaxy, which is our nearest large neighbor, is a spiral galaxy and looks even more pristinely spiral than ours, more perfect, more geometrically arranged. They're gorgeous. They're almost too perfectly organized looking, like someone sat down with a compass and a geometric pencil and drew them. Like they were designed by an intelligent architect with aesthetic sensibilities. But here's where it gets weird. Those arms shouldn't really exist the way we see them. The winding problem. That's the technical name, and it's stumped astronomers for literally decades. This is one of those problems that seems simple until you actually do the math, and then it blows your mind, and you realize you were missing something fundamental about how the universe works. Here's the issue. If a spiral galaxy just rotated uniformly like a record on a turntable, The arms should wind up so tightly over billions of years that they disappear into the center. Imagine you took a piece of paper, drew a logarithmic spiral on it, one of those spirals that gets tighter and tighter as you move toward the center, and then spun the paper. The spiral would get wound tighter and tighter as it rotates, faster and faster, accelerating until it was basically just a dot at the center. The spiral structure would become unrecognizable within millions of years. That's what should happen to spiral galaxies if they're just rotating rigidly. The arms should spiral inward until the structure becomes completely wrecked. But that's not what we observe. Spiral galaxies maintain their spiral structure for billions of years. The arms are still there. The pattern is still clear. The structure is still recognizable. How is this possible? So what's actually happening? And this is cooler than the simple answer. The arms aren't actually made of the same stars over time. This is the mind-bending part. Stars pass through the arms like traffic through a city. The arms are more like traffic jams in space, regions of higher density that stars cruise through and then move past. The density wave persists, even though the stars making up the wave are constantly changing. It's not that the same stars stay in the arms, it's that there's always a traffic jam there. Think of it like a traffic jam on a highway during rush hour. Individual cars come and go, but the jam persists for hours or sometimes days. Some cars enter the jam at the back, get stuck in it for a while, and then exit at the front. But to an observer, it looks like the jam is a permanent structure. It looks like the jam is a real object that exists in space. But it's not. It's a pattern. It's a wave. That's what the spiral arms are. They're standing waves in the galactic disk. The stars move through them like cars through congestion. Some stars pass through and out, others enter. But the pattern persists. The density wave doesn't dissipate or spiral in. It stays where it is, and stars flow through it, which is somehow cooler and weirder at the same time. It means that if you were a star living in the Milky Way, if you had consciousness and awareness and could think about your journey through space, you'd periodically pass through the dense spiral arms every couple 100 million years. You'd experience a burst of star formation and cosmic events and gravitational chaos. Massive stars would be born around you. They'd fuse their hydrogen and explode as supernovae, lighting up the sky. Planets would form in the dense gas, X-rays and radiation would fill space. New elements would be created in those supernovae. And then you'd cruise out into the less dense regions between the arms for a while, and things would quiet down. Your neighborhood would change dramatically every few 100 million years. Stars around you would be born and die. The chemistry of your local region would change. The radiation environment would shift. New planets would form. Some would become habitable. And then you'd move into the less crowded regions and things would quiet down again. It's a rhythm, a cosmic rhythm that plays out over millions of years. Every time our solar system passes through a spiral arm, it experiences this chaos and then calm. Now, galaxies come in different shapes, and the shapes tell stories about the galaxy's history and past, what it's experienced, what it's gone through. You've got spirals like ours, grand spirals with 2 or more arms, creating that beautiful pinwheel pattern that looks like a cyclone or a cosmic hurricane, or barred spirals that have this thick bar structure running through the middle like a cosmic railroad or a cosmic spine. That bar is like cosmic awkwardness in physical form. a concentration of stars and gas forming a bar across the galactic center, often with spiral arms extending from the ends of the bar. These barred spirals are actually pretty common. Maybe half of all spiral galaxies are barred spirals. Astronomers still debate whether the Milky Way's central bar formed naturally out of the disk due to gravitational instabilities, the disk becoming unstable and creating a bar spontaneously, or whether it was created by some long-ago interaction with another galaxy that left its mark. A collision with a dwarf galaxy could have created the bar. We don't really know. It's still a mystery about our own galaxy, about the structure we live in. You've got elliptical galaxies that range from nearly spherical, like cosmic basketballs, to weirdly elongated, like cosmic footballs of varying oblateness and eccentricity. Some ellipticals are almost perfectly round, others are stretched into cigars or footballs, or even more extreme shapes. Ellipticals can be thousands of times more massive than spiral galaxies, with enormous collections of hundreds of billions or even trillions of stars. The galaxy M87, for instance, is an elliptical galaxy with probably trillions of stars. It dwarfs the Milky Way. It's massive. And at its center is a supermassive black hole that's billions of times the mass of the sun. We actually photographed the shadow of this black hole in 2019. It was the first ever image of a black hole. It was mind-blowing. And you've got irregular galaxies that look like someone took scissors to them. Jagged edges, strange shapes, no real symmetry, no clear organization. These usually exist because they got too close to another galaxy and gravity got awkward about it, literally. Two galaxies interacting tidally, pulled and stretched and distorted by each other's gravity until they look mangled, which tells us something important. The shape of a galaxy tells us its history. Each type forms under different conditions and tells a different story about the galaxy's past, what it's experienced, what it's been through. Elliptical galaxies used to be thought of as dead galaxies, just burnt-out husks where all the star formation had long since stopped. Fossil galaxies, leftovers from the early universe, museum pieces, relics of the past. But that's not really true. They can still have star formation happening inside them. It's just happening way slower and less visibly than in spirals. Sometimes ellipticals can have starbursts of their own, times of intense star formation. The reason elliptical galaxies exist in the first place is usually violent. When two galaxies collide and merge, and this happens all the time on cosmic timescales, especially in the early universe when things were more densely packed and collisions were more frequent, the result is almost always an elliptical galaxy. The spiral structures of both galaxies get destroyed. The organization gets wrecked. Galaxy mergers are common. They're still happening today. Astronomers estimate that the Milky Way has merged with other galaxies multiple times in its history. We've cannibalized smaller galaxies. We've absorbed their stars into our halo. The merger process is dramatic and violent and spectacular. Two galaxies start drifting toward each other due to mutual gravity. They're pulled by Newton's law of gravitation. Each is attracted to the other's mass. As they get closer, tidal forces start stretching each galaxy like taffy. Imagine two massive objects pulling on a galaxy from different directions, stretching it, deforming it. The galaxy gets torn and distorted. The spiral structure gets mangled and torn apart. Stars that were orbiting in neat, organized planes start moving in random directions. Gas clouds collide with each other at tremendous speeds, possibly thousands or millions of kilometers per hour. They heat up to extreme temperatures, sometimes millions of degrees Kelvin. At these temperatures, electrons are ripped away from atoms. You get plasma. The colliding gas clouds start forming new stars in bursts, lots of new stars forming all at once. This is called a starburst event. The two galaxies pass through each other, and I want to emphasize that they pass through each other because space is so empty that individual stars almost never actually collide, even as the galaxies merge. Individual stars could pass within miles of each other without colliding, but gravitationally, it's chaos. The merged gravitational field of both galaxies acts on all the stars, and they get flung this way and that. Some get accelerated to tremendous velocities and flung outward. The system becomes roiling and chaotic. It's a turbulent, energetic time. It's spectacular. Then, after the two galaxies pass through each other, gravity pulls them back together. They swing around and collide again. More chaos. Another pass through. Multiple interactions over millions of years. Some of the most beautiful things in the universe are in the process of being destroyed. Gradually, over millions of years, through multiple passes, the system settles down. The stars settle into new orbits. The merged galaxy structure stabilizes. You're left with an elliptical galaxy, a giant ball of stars with no particular organization, all moving in random directions relative to each other in a seemingly chaotic dance, though really governed by gravity. If it's a really massive merger, you get a giant elliptical. These can be some of the largest structures in the universe, containing trillions of stars, massive structures floating in the void, orbiting around the centers of galaxy clusters. The most massive galaxies we know of are giant ellipticals. Ellipticals can be more than 1,000,000 light-years across. The Andromeda Galaxy is a spiral. The Milky Way is a spiral. The Triangulum Galaxy is a spiral. These are all nearby neighbors in cosmic terms, all part of the local group, and they're all the same shape, which actually raises an interesting question. Is there some reason spirals are stable or favorable over other shapes? Do spiral galaxies last longer? Or are we just seeing a selection effect where our neighborhood happens to have a bunch of spirals? Is our local region typical or atypical? The universe is complicated like that. Sometimes what you think is a universal principle turns out to just be a local pattern. Sometimes you realize your neighborhood is weird compared to the rest of the universe, and that opens another loop. What does the broader universe look like beyond our little corner? Irregular galaxies are usually the result of mergers or close encounters that are still ongoing. The Large Magellanic Cloud and the Small Magellanic Cloud are these irregular satellite galaxies orbiting the Milky Way. There are companions in space orbiting around us like the moon orbits Earth, but much, much larger and much farther away. And they're getting ripped apart by our galaxy's gravity, slowly but inevitably being pulled into streamers and trails of gas and stars. The tidal forces are stretching them out. In a few billion years, they won't exist as distinct structures anymore. They'll just be part of the Milky Way. They'll have been completely incorporated into our galaxy, their stars becoming part of our halo, their gas mixing with ours. And that's kind of sad when you think about it. These galaxies that have existed as separate entities for billions of years, that have their own histories and their own identities, are in the process of being destroyed by gravitational tides, and there's nothing they can do about it. Gravity doesn't care about your history. It doesn't care about your identity as a distinct galaxy. It doesn't care about your beauty or your uniqueness. It just does what gravity does. It pulls, it organizes, it destroys. It's indifferent, it's powerful. It's the force that shapes everything. But here's where it gets really interesting, where we start moving up the hierarchy to larger and larger scales that contain more and more galaxies and more structure, more and more of the universe. Galaxies don't exist alone. They cluster together. They're attracted to each other by gravity. They form groups. They form networks. Our Milky Way is part of something called the local group, which sounds like maybe an indie band or possibly a support group for people who live near each other, but is actually a collection of about 80 galaxies bound together by gravity. 80 distinct galaxies, all held together in a gravitationally bound system, all orbiting around a common center of mass, though the center of mass might not be exactly where you'd expect. Some galaxies moving toward that center, some orbiting around the periphery. It's a dynamic system. Things are moving, things are changing. Andromeda is in there with us. It's the nearest major galaxy to us, about 2.5 million light years away. By cosmic standards, that's basically next door. It's like living in two houses on the same block, close enough to visit, close enough to see what the neighbor's doing. To give you a sense of scale, 2.5 million light years is the distance light travels in 2.5 million years. That's longer than humans have existed as a species. Humans have only been around for about 300,000 years. So light from Andromeda takes almost 10 times longer to reach us than humans have existed on Earth. It takes light a quarter of the time humans have existed just to bridge the gap between us and our nearest galactic neighbor. And that's considered basically next door in cosmic terms. It's mind-bending. It's hard to wrap your head around. The scale is difficult to comprehend. Andromeda is actually bigger than the Milky Way, or at least it was considered bigger for a long time. It's got roughly 1 trillion stars compared to our maybe 2 trillion stars. Wait, actually, I need to correct myself again. Our newest estimates from recent surveys using newer telescopes suggest the Milky Way might have more stars than Andromeda after all. The numbers keep changing as we get better at counting and as our instruments improve. The point is, they're comparable in size, which is interesting because it means when they collide, it'll be more of an equal merger situation than the Milky Way eating some smaller galaxy. It's going to be a cosmic collision between two titans, two heavyweights meeting in the cosmic ring. A cosmic merger of giants. And this brings us to one of the most important questions in cosmology. What happens when our galaxy collides with Andromeda? And yeah, Andromeda and the Milky Way are on a collision course. They're gravitationally bound to each other. They're part of the same system, the local group, and they've been drifting closer over billions of years. The space between us is shrinking. The gravitational attraction is pulling us together. In about 4.5 billion years, give or take a few hundred million, our estimates keep changing as we get better at measuring, as we get better instruments. They're going to merge into one massive elliptical galaxy. We don't have a great official name for it yet, but some astronomers have jokingly suggested Milkdromeda, or Andromedky Way, or Milkomeda, which is adorable and probably won't stick in scientific literature. The merger isn't going to be instantaneous. It'll take millions of years to complete. It'll be a slow, gradual process. First, they'll get close enough that tidal forces start distorting both galaxies significantly. The stars on the near side of each galaxy will be pulled harder than the stars on the far side, stretching the galaxy like taffy. The spiral structure will start to become disrupted. The arms will be torn. Then they'll pass through each other. And this is crucial. They'll literally pass through each other because even though the galaxies are huge, hundreds of thousands of light years across, space is so empty that the individual stars won't collide. Stars will pass within light years or even hundreds of kilometers of each other without hitting, because space is that empty. The probability of two stars actually colliding is essentially zero. Then they'll swing around and come back together. Eventually, after several passes over millions of years, maybe 3 or 4 major passes, they'll settle into one unified structure. A merged megagalaxy. A new galaxy born from the collision of two great galaxies. It's beautiful and tragic at the same time. The odds of our solar system getting destroyed in that collision are actually pretty low because space is so mind-breakingly empty. Galaxies are huge, but they're separated by such insane distances that even when they collide, most of the stars pass right by each other. The density of stars in a galaxy is so low that the probability of any two stars actually colliding is essentially zero. However, our solar system could get bumped into a very different orbit. It could end up in a region with much higher stellar density, much closer to the galactic center, where gravitational forces would be much stronger and temperatures would be higher due to proximity to more stars. Or it could end up in a region with much lower density, far from the center, isolated in the outer halo where it would be essentially alone, which would have all sorts of gravitational and thermal consequences for us. It would change our night sky dramatically. The night sky from Earth billions of years from now could look completely different depending on where we end up. Currently, we see the Milky Way's disk as a band across the sky. In the future, we might see it as a completely different structure. We might see Andromeda as a separate object for a while before they fully merge, watching it grow larger and larger in the sky year by year, watching two galaxies slowly become one. Our descendants would witness cosmic change on a timescale longer than the existence of human civilization. They would see their universe transform. Actually, there's a decent chance our solar system gets ejected entirely from the merged galaxy during the collision. Gravitational interactions during mergers can fling stars outward at incredible velocities. Stars that were orbiting peacefully can suddenly be accelerated to thousands of kilometers per second. We could end up in the intergalactic void, orbiting the merged galaxy, but essentially alone. Just our solar system in empty space. Our Oort cloud, the cloud of icy bodies surrounding our solar system, reaching out into the darkness, which would be both terrifying and probably pretty beautiful in a dark, isolated way. Alone, but safe. Isolated, but intact. We'd be an island in the cosmic ocean. But which scenario is the real future for us? That's a mystery we can't solve. The merger depends on precise dynamics, on the exact angles and velocities and mass distributions, and there's too much uncertainty to predict exactly where we'll end up. But that's billions of years in the future. What's happening now, in our current cosmic moment, which is itself the result of 13.8 billion years of cosmic evolution, is that the universe is structured. And if we zoom out from our local region and look at bigger and bigger scales, the structure becomes even more apparent. It becomes almost overwhelming. The organization becomes even more striking. It structures all the way up, with each level more organized and larger than the last, hierarchies upon hierarchies. Local groups like ours are part of larger structures called clusters. A galaxy cluster is hundreds or thousands of galaxies, all bound together by gravity, separated by only a few million light years from each other. Within a cluster, gravity dominates everything. It's the dominant force shaping the region. The galaxies are trapped in each other's gravitational wells. They orbit around the cluster's center of mass. Some fall inward toward the center. Some orbit around the periphery. It's a dynamic system, constantly changing over cosmic time, with galaxies occasionally colliding and merging. Clusters aren't static. They're evolving. They're changing. They're alive in a physics sense. And which brings us to one of the biggest mysteries in astronomy. Thanks for watching. The Virgo cluster is a pretty famous one. It's got over 1,300 galaxies, and it's only about 65 million light years away, which means we can see it in decent detail from Earth with telescopes. With a good telescope, you can actually make out individual galaxies in the Virgo cluster. They look like faint fuzzy patches if you're looking at them through a telescope, but they're there if you know where to look. Each one is a galaxy containing potentially hundreds of billions of stars. All those stars in all those galaxies, and from Earth, they just look like faint smudges of light. It's humbling. It makes you realize how vast the universe is and how small we are in it. We're not just small compared to galaxies. We're small compared to clusters of galaxies. We're nested within layers upon layers of structure. The gravitational pull of the Virgo cluster is actually pulling our local group toward it right now. Over billions of years, we're slowly being drawn into its gravity well. The Virgo attractor is the name for the gravitational anomaly that's pulling us. Eventually, far in the future, the local group will merge with the Virgo cluster. Andromeda will merge with the Milky Way first, creating a massive elliptical galaxy. And that merged galaxy will join the Virgo cluster. Everything will become one massive structure, one huge cluster containing thousands of galaxies. Mergers happen at every scale. There's also the Coma cluster, which is this massive dense collection of thousands of galaxies that made astronomers realize something was deeply, fundamentally weird about how the universe works. And the Fornax cluster, and the Hercules cluster, and the Perseus cluster. There are hundreds of known galaxy clusters, and probably countless more too distant or too faint for us to see yet. Each cluster is a gravitationally bound system containing thousands of galaxies. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, trying to figure out how fast the galaxies were moving. He wanted to measure their velocities and use those to calculate how much mass would be needed to keep the cluster bound gravitationally. This is based on a principle from orbital mechanics. If you know how fast something is moving and how far it is from the center of mass, you can calculate how much mass must be at that center to keep it in orbit. It's basic physics. Newton figured this out in the 1600s, so Zwicky measured the velocities of galaxies in the Coma cluster using the Doppler effect. The way light shifts toward red or blue depending on whether something is moving away from or toward you. You've probably heard of this effect with sirens. When an ambulance approaches, Its siren sounds higher pitched because the sound waves are compressed. When it moves away, the siren sounds lower pitched because the sound waves are stretched. Light works the same way. Light from an object moving toward you is shifted toward the blue part of the spectrum. Its wavelength decreases. Light from an object moving away is shifted toward the red part. Its wavelength increases. This is redshift. By measuring this shift in light from galaxies, by looking at spectral lines and seeing how much they're shifted toward red, astronomers can determine how fast those galaxies are moving away from us. He got his measurements, he did the math, and the numbers didn't add up. The galaxies were moving way too fast. By all the laws of physics, by Newton's laws of gravitation, the cluster shouldn't hold together. If the galaxies were really moving that fast, they'd have enough kinetic energy to escape the cluster's gravity. They'd fly apart. There wasn't enough visible matter, enough stars and gas that we could see, to provide the gravitational glue needed to keep everything in place. The escape velocity was too high. The kinetic energy was too great. It didn't make sense. So Zwicky proposed something radical. There must be matter we can't see, something invisible, something that doesn't interact with light, something that only interacts through gravity. He called it dark matter, and basically everyone ignored him for 40 years, not just ignored, dismissed, mocked, considered him crazy, said he was doing bad science, because that sounded like complete nonsense. Invisible matter? That can't be right. It violates common sense. It violates Occam's razor. Don't multiply entities beyond necessity. Surely he made a measurement error. Surely there's a simpler explanation. Surely the universe doesn't consist of invisible stuff we can't detect. It seemed absurd. It seemed like bad science, pseudoscience, fringe thinking. But Zwicky was right. Can you imagine? This guy figures out that 85% of all matter in the universe is invisible, fundamentally changing our understanding of the cosmos, and people are just like, nah, you probably made a math error. The data's probably bad. Let's move on and ignore this crazy idea. It's one of the wild cases in science where the right answer sounds so ridiculous it gets rejected for decades. The scientific establishment literally rejected the truth because it sounded too weird. Zwicky wasn't even entirely sure what dark matter was. He just knew that something had to be there to make the math work. He called it dark matter because it's dark. Invisible to light, it doesn't interact with electromagnetic radiation. And here we are almost a century later, and we still don't actually know what dark matter is. We've spent nearly 100 years studying it, building experiments to detect it, running simulations to understand its behavior, and we still can't figure out what it is. It remains one of the deepest mysteries in physics, one of the greatest unsolved problems. We don't know what 85% of the matter in the universe is made of. That's insane. That's beautiful. That's something worth dedicating your life to solving. Then, in the 1970s, an astronomer named Vera Rubin made observations of how fast stars were moving in the outer regions of galaxies. She was using the Doppler effect again, measuring the spectral lines of light from stars at different distances from the galactic center. She wanted to understand the rotation curves of galaxies, how the orbital speed of stars changes as you move outward from the galactic center. And she found the same problem that Zwicky had found decades earlier. The math didn't work. The outer stars and galaxies were moving too fast. They should have been flung outward by centrifugal forces, escaping the galaxy's gravity. But they weren't. Something was holding them in place, something invisible, something massive. Rubin's work was meticulous and well documented and rigorous. She had data from multiple galaxies showing the same pattern. Her measurements were careful and precise. She was thorough. She repeated measurements. She checked her work. And when other astronomers looked more carefully at clusters of galaxies, the same issue kept showing up. We couldn't see enough matter to explain the gravity. The math always came out the same way. There was more gravity than there should be given the visible matter. Dark matter wasn't just a fringe theory anymore. It wasn't something a few cranks believed. It was an absolute requirement of cosmology. It was the only way the universe as we observe it could actually exist without violating the laws of physics. You couldn't explain the observations without it. Vera Rubin's work was so important that it basically established dark matter as mainstream science. She won tons of awards and recognition for this work. She became one of the most respected astronomers in the world. She was a pioneer in a field dominated by men, and she broke through barriers and made discoveries that changed our understanding of the universe. But here's the tragic part. The part that makes me sad. She was never awarded the Nobel Prize for this work, which was a controversial snub in the astronomy community. Many scientists thought she should have won it. She deserved it. She passed away in 2016 at age 88. And Nobel Prizes aren't given posthumously, which meant she would never get that particular recognition. But her work fundamentally changed how we understand the universe. Every cosmologist, every physicist, every person studying structure in the universe is building on the foundation that Vera Rubin established. Her legacy is the understanding that dark matter exists and dominates the universe. She proved it through careful observation and rigorous analysis. Here's the truly weird part about dark matter. It makes up about 85% of all matter in the universe. Everything you can see, every star, every planet, every atom in your body, every galaxy cluster, every cosmic structure visible to our telescopes, is just 15% of the matter. We're literally living in a universe made of something we can't directly observe. Something that doesn't interact with light at all. It's completely invisible. It doesn't emit light, doesn't absorb light, doesn't reflect light. Light passes through it without interacting. It's completely transparent to electromagnetic radiation. The only way we know it exists is through gravity. We're inferring its entire existence from gravitational effects on visible matter. And here's the really mind-bending part. Dark matter is what shapes the universe. It's not a minor component that we can ignore. It's the dominant component by mass. The visible galaxies and clusters are just the light traces of dark matter structures. Dark matter is the architecture. We're seeing the scaffolding that dark matter built, highlighted by the 15% of matter that shines. We're seeing the structure of the universe outlined by starlight, but the actual structure, the thing holding it all together, is invisible. Scientists have run all sorts of experiments, trying to detect dark matter directly. There are massive detectors deep underground, sometimes a mile or more underground, shielded by miles of rock and layers of water from cosmic rays that would interfere with the measurements. Cosmic rays are constantly bombarding Earth from space, and they'd create noise in the detectors if they weren't shielded. These experiments are waiting patiently to catch a dark matter particle bumping into a regular atom. Detecting such a collision would create a tiny signal. A few atoms would recoil from the impact. The detectors are sensitive enough to pick up this recoil, sensitive to individual atomic nucleus collisions. These experiments have been running for decades now and haven't found anything definitive yet, which either means dark matter is really, really hard to detect, or we don't actually understand what dark matter is in the first place. Probably both. Maybe dark matter isn't a particle at all. Maybe it's something we haven't even thought of yet. The leading candidate is something called WIMPs, weakly interacting massive particles. These would be particles that barely interact with regular matter at all, which is exactly why they're so hard to find. They could be passing through you right now and you'd never notice. Trillions of dark matter particles could be flowing through Earth every second like neutrinos, and we wouldn't feel a thing because they don't interact electromagnetically. They only interact gravitationally. But there are other candidates too. Axions are another popular theory. Hypothetical particles originally proposed to solve a different problem in physics, something about CP symmetry violation, but which could potentially be dark matter. Primordial black holes, tiny black holes formed in the early universe, could theoretically be dark matter. Sterile neutrinos, neutralinos, there are dozens of candidates. We just don't know. It's one of the most frustrating and fascinating frontiers of modern physics. We know dark matter exists. We know it makes up most of the matter in the universe. But we don't know what it is. That's amazing. That's humbling. That's an open question waiting to be answered. Dark matter's gravitational influence is massive, though, and it basically sculpts the entire large-scale structure of the universe. Think of it like this. Regular matter, the stuff we're made of, the stuff we can see, is like a visitor to a house. Dark matter is the house itself. The house determines where the visitor can go, what they can do, the whole shape of their existence. The house's walls, doors, and structure constrain everything. You can't walk through a wall. You can only move through the doors. Your path is determined by the structure of the house. That's the relationship between dark matter and visible matter. The structure determines what's possible. When you zoom out even further and look at the structure of the universe on the absolutely largest scales, when you step back and look at regions containing thousands of galaxy clusters, thousands of clusters containing thousands of galaxies each, you start to see something that looks less like a random distribution and more like a cosmic architecture that's almost geometric in its weirdness. It's organized, it's structured, and the patterns are so clear that you can't deny they're real. This is the cosmic web, and this is where we're heading next, so keep watching. Thanks for watching. If you could somehow map out the distribution of all the galaxies across billions of light years, and thanks to projects like the Sloan Digital Sky Survey and increasingly sophisticated telescopes, we're actually getting pretty good at this. You'd see that they're not evenly spread out across space randomly. Instead, they're organized into structures called filaments and sheets, with enormous empty regions called voids in between. This large-scale structure is sometimes called the cosmic web or the cosmic network. It's probably the most visually stunning map in all of science when you actually look at it. It looks like neural tissue in a brain, all these interconnected pathways and patterns. It looks like the branches of a tree, fractal patterns repeating at different scales. It looks like some kind of three-dimensional web spun across the cosmos by some cosmic spider. It looks almost alive, which is weird because it's the opposite of alive in most conventional senses, but it has this organic, growing quality to it that's hard to shake. The filaments are basically highways of galaxies, regions where thousands or tens of thousands of galaxies are clustered along these thin, elongated structures that can stretch for hundreds of millions of light years. Imagine a thread made of galaxies, stretching for hundreds of millions of light years, populated with clusters and groups of galaxies. If you could somehow travel along one of these filaments, which you can't because space doesn't work that way and the distances are incomprehensibly vast, you'd pass through cluster after cluster after cluster, thousands of galaxies, billions of stars, all of it arranged in this linear structure. There'd be gravitational chaos happening constantly as galaxies merge and interact and collide. Between the filaments are voids. These aren't just empty spaces where you might find the occasional lonely galaxy. They're truly, almost completely empty. We're talking about regions billions of light years across that contain essentially no galaxies at all. They're not perfectly empty. There might be a few isolated galaxies floating in the void. But compared to the filaments, they're cosmic deserts. Cosmic deserts, billions of light years across with almost nothing in them. If the filaments are the cell walls of this cosmic structure, the voids are the empty space inside the cells. If you were somehow alive and traveling through a void, impossible given the distances and the time it would take, you might not encounter another galaxy for billions of light years. You'd be alone in a vast, cold emptiness, surrounded by nothing but darkness and the slow expansion of space itself. It's like the universe is organized into this cosmic foam, where the structure is in the walls, the filaments, and the empty space is actually empty. For a long time, astronomers didn't really understand why the universe would organize itself this way. It seemed weird. Why wouldn't galaxies be more evenly distributed? Why this strange web pattern with all these filaments and voids? But it turns out it has everything to do with how gravity and dark matter interact on the largest possible scales, which is one of the coolest explanations in all of cosmology. And I want to walk you through it because it's beautiful. Back in the early universe, right after the Big Bang, and I mean really right after, like the first fraction of a second after the moment of creation, when the universe was incomprehensibly hot and dense, everything was in a state of extreme density. It wasn't just very hot, it was hotter than anything could possibly survive in. It was hotter than the cores of stars by orders of magnitude. It was hotter than anything that would exist for billions of years afterward. And it was expanding rapidly, cooling as it expanded. As it expanded and cooled, weird quantum things were happening at the tiniest scales. In the first fractions of a second, there were bizarre processes happening that we still don't fully understand. The laws of physics as we know them might have been different or incomplete at those energies. But one of the most important things that was happening was the creation of tiny quantum scale fluctuations, impossibly small variations in density scattered throughout the universe. These fluctuations were probably created by quantum uncertainty, which is the principle that at the quantum level, nothing has a definite value. Everything is kind of fuzzy and probabilistic until you measure it. Things can pop in and out of existence briefly. Energy can fluctuate. Uncertainty is built into the fabric of reality at the smallest scales. This is the quantum vacuum. And in the early universe, these quantum fluctuations created tiny density variations, places where the density was slightly higher than average and places where it was slightly lower. These variations were incredibly small at first, differences of 0.001% or even smaller, incomprehensibly small, so small that they shouldn't matter. But over time, gravity amplified these fluctuations. And this is the key to understanding cosmic structure. This is where the universe went from being almost perfectly uniform to being structured. Regions that were even slightly denser than average pulled in more and more matter through gravitational attraction, like cosmic gravity wells that got deeper and deeper. The denser the region, the more matter it attracts. The more matter it attracts, the denser it becomes. It's a runaway process, exponential growth. A region that starts out 0.1% denser than average attracts more matter, which makes it 0.2% denser, which attracts even more matter, and so on. The process accelerates. Over billions of years, this led to the creation of the cosmic web we see today. It's a process called gravitational instability. Small perturbations in density grow over time. The universe was born with tiny random fluctuations baked in from quantum mechanics. Those fluctuations amplified through the universe's history. And now, 13.8 billion years later, you've got galaxies and clusters and filaments and the entire cosmic web. Everything, all the structure, all the organization, it all emerged from tiny quantum fluctuations in the simple force of gravity. The filaments form along the densest regions where huge amounts of dark matter accumulated early on due to this gravitational amplification. Gravity pulled dark matter together into dense regions. Those dense regions attracted even more dark matter. Visible matter accumulated in these dense regions too, forming galaxies. Galaxies cluster in the knots where filaments intersect, where the gravitational pull is strongest from multiple directions, where multiple filaments meet. You get these nexus points where multiple filaments converge, creating regions of enormous density, enormous concentrations of matter. And vast voids are where the matter was initially depleted, regions that started out slightly less dense than average, and then had all their matter pulled out into nearby filaments by gravitational attraction. The matter migrated away, left behind emptiness, loneliness, the void. What's fascinating is that the dark matter didn't know it was organizing itself into this pattern. There was no blueprint, no cosmic architect drawing up plans. It's not like there's some master plan written into the universe, some intelligent designer laying out the cosmic web with intention and purpose. It's just what happens when you have gravity, dark matter, and 13.8 billion years. That's all. Gravity is this incredibly simple force. It's literally just mass telling space how to curve, as Einstein described it. Mass and energy warp the fabric of space-time. Objects follow the curves in space-time. That's gravity. It's beautiful in its simplicity. But when you apply it at cosmic scales and let it run for eons, it creates structures of breathtaking complexity. Order emerges from simplicity. Pattern emerges from randomness. Complexity emerges from simple physical laws. It's almost like the universe is this beautiful machine that organizes itself through the simple action of gravity. No intelligence needed, just physics. I got really deep into this stuff in college. I took a cosmology class that was probably more than I could handle at the time. It was a graduate level course, and I was an undergrad, but I crashed it anyway because I was obsessed. I was up at like 3 a.m. in the library reading papers about structure formation, n-body simulations, where physicists literally simulate the universe with billions or even trillions of particles to see how structures form. They set up the initial conditions, put dark matter particles in a cube of space, give them the density fluctuations that we observe in the cosmic microwave background, simulate gravity over cosmic time, and watch what happens. Dark matter distribution models, cosmic variance, perturbation theory, all of it. Papers full of mathematics that I could barely understand but was determined to work through anyway. Differential equations, Fourier analysis, linear algebra. I was trying to understand the universe from first principles, and I remember this specific moment where it clicked for me. I was reading about how computer simulations of structure formation always produce these filaments and voids and cosmic web patterns, regardless of the specific parameters used. Whether you change the amount of dark matter slightly, or the initial density fluctuation amplitude, or the expansion rate, or the properties of dark energy, you always got this same general pattern emerging. Filaments, voids, a cosmic web. It seemed universal. It seemed inevitable. It seemed like this was just what the universe does. And I realized something profound. The universe isn't designed. It's not architected in the way my dad was imagining back when I was 15, lying in the backyard looking at the Milky Way. But it is structured, and the structures emerge from nothing more than physical laws playing out across inconceivable scales of space and time. No designer needed, no intelligence required, no intention, just physics, just gravity and dark matter and time. That's actually more beautiful than if some cosmic architect had drawn it up. It's elegant in this completely impersonal physics-based way. The universe organized itself through gravity, through dark matter, through time. And now, billions of years later, we're here, made of stardust, made of matter forged in stars, made of consciousness somehow emerging from physics, and we're able to look back and understand the mechanism that created us. We can understand how the universe works. We can read its history. We can predict its future. Now, there's a philosophical thing happening here that I think is worth sitting with for a second, because this is the kind of thought that should make you pause. It's the kind of thought that changes how you see things completely. It's the kind of realization that should change your entire perspective on your place in the universe. For most of human history, the night sky was mysterious and transcendent. We made up stories about gods and destiny written in the stars. We saw constellations and believed they meant something about our lives, about fate, about the future. We threw coins in wells and made wishes to the stars. We danced under moonlight and told stories about gods living up in the heavens. We looked up and felt small and insignificant and filled with wonder. The cosmos was magic. It was sacred. It was beyond our understanding. It was beyond our reach. We could only wonder and imagine and make up stories to explain what we saw. Then astronomy got better. Telescopes were invented. We could see more stars. We could measure their distances. We developed spectroscopy and could see what elements were in stars. We learned to measure velocities using the Doppler effect. And we realized the stars are just massive balls of fusing hydrogen and heavier elements. Just thermonuclear reactions happening in distant spheres of plasma. That was deflating in some ways. The romance kind of went out of stargazing once you realized it was just physics. We learned that planets orbit stars, that stars orbit galaxies, that galaxies are just huge collections of matter following the laws of physics. Everything could be explained by physics, everything. The magic seemed to evaporate when we understood the mechanism. But then we went even further, and we realized something even more mind-bending than we expected. We realized that the entire cosmic structure, everything visible, everything sensible, every galaxy, every star, every planet, every atom, is actually embedded in a substrate of dark matter that we don't understand, organized by forces we're still trying to comprehend, following patterns that emerge from simple mathematics applied across billions of years and billions of light years. The universe is made of something we can't see, arranged in ways we're still trying to figure out, and it's been evolving and organizing itself for nearly 14 billion years. And somehow, that's even more transcendent than the old myths about gods and destiny, because it means the universe doesn't need a god to be beautiful. The math is enough, the physics is enough, the complexity that emerges from simplicity is enough, the self-organization of matter through gravity is enough. That's a weird kind of spiritual experience, in my opinion, realizing that wonder doesn't require magic, just reality, just the laws of physics playing out, just mathematics describing nature. It's beautiful, it's profound, it's awe-inspiring. It makes me feel small and significant at the same time. But here's the thing that blows my mind. We're only seeing part of the picture. We can map the visible universe, the part we can see because light from it has had time to reach us since the Big Bang. The visible universe has a radius of about 46.5 billion light years. That's the edge of what we can currently observe from Earth. But the actual universe is probably way bigger than that. The actual universe might be so big that our entire cosmic web, with all its filaments and voids and billions of galaxies and trillions of stars, is just local. A neighborhood, a suburb of some incomprehensibly larger universe, which opens up this insane question. Are there other cosmic webs? Other structures we can't see because their light hasn't reached us yet? Are there other filaments the size of our local filaments, other voids the size of our local voids, stretching beyond our cosmic horizon into regions that might as well be unreachable? What do they look like? Are they arranged differently? Do they have the same filament and void pattern that we see? Or does structure formation create infinite variations? Is the pattern universal, or is it specific to our region? Scientists have been playing around with simulations, using our understanding of cosmology and the laws of physics to run virtual universes and see what structure formation looks like under different conditions. Different starting conditions, different amounts of dark matter, different ratios of regular matter to dark energy, different physical constants. What if gravity were stronger? What if gravity were weaker? What if dark energy didn't exist? What would the universe look like? And you know what's weird? It almost always looks weirdly similar to ours. You almost always get filaments and voids. You almost always get this cosmic web structure. The details might change. The filaments might be thicker or thinner. The voids might be bigger or smaller. But the general pattern is always there, which suggests that maybe this is just what happens when you combine gravity and dark matter and time. Maybe it's inevitable. Maybe the structure we see isn't unique or special. It's just what physics produces when you let it run. It's the natural outcome of these forces. This is what the universe does. Given gravity and dark matter and billions of years, this is what you get. You get a cosmic web. You get filaments. You get voids. It's written into the laws of physics, which is either deeply comforting or deeply unsettling, depending on how you look at it. On one hand, it means that wherever there's matter and dark matter in the universe, this same structure emerges. The universe is self-organizing into patterns. Beauty and structure emerge naturally from the laws of physics. We don't need special conditions or special initial conditions, just gravity and time and dark matter, and you get structure. On the other hand, it could mean that our observations are limited enough that we're missing some alternative possibilities. We don't really know. We can only see what we can see, and our theories are based on what we observe. There might be other types of structure that don't show up in our local region. There might be cosmic anomalies and weird structures that we haven't discovered yet because they're beyond our horizon or too different from what we expect to recognize. And we're blind to most of the universe. We can only see ordinary matter, which is 15% of the matter, and we can see it only if it's emitting light or reflecting light. Stars emit light. That's how we see them. Galaxies emit light from their billions of stars. That's how we see galaxies. Hot gas clouds emit light. But there's a ton of dark matter that we can infer is there from gravity, but that we literally cannot see directly. We've detected it indirectly through something called gravitational lensing, the way light bends around massive objects due to gravity. But we can't see the dark matter itself. The light bends around it like water flowing around a rock, and we can map the shape of the rock by how the water flows. But we can't see the rock directly. We can only see its effect on light, and then there's dark energy, which we know even less about. Dark energy makes up 68% of the energy density of the universe, and we have almost no idea what it actually is. It seems to be accelerating the expansion of the universe itself, pushing space apart faster and faster. But we can't see it. We don't know how to detect it directly. We only know it exists because we've measured the expansion of the universe and found that it's speeding up, which shouldn't happen according to old models of gravity. Something had to be causing this acceleration, so we called it dark energy. But honestly, we're just naming our ignorance at this point. We're saying, there's this phenomenon we observe. We don't know what causes it. Let's call it dark energy. It's a placeholder for our lack of understanding. So when we look at the cosmic web and we think we're seeing the structure of the universe, we're really seeing only the scaffolding that dark matter built, traced out by the 15% of matter we can actually detect. It's like we're in a house made of dark matter and dark energy, lit by a few scattered candles representing the stars and galaxies. We can see by candlelight where the walls are, but we can't see the walls themselves. We're blind to most of the universe. Most of existence is hidden from us. Let me give you a concrete example of something wild in the cosmic structure. There's something called the Great Wall, or the Hercules Corona Borealis Great Wall, if we're being technical about it. It's a massive filament of galaxies that extends for about 10 billion light years. That's roughly the distance from our solar system to the edge of the observable universe. This thing is enormous. It's one of the largest known structures in the universe. It's a filament of galaxies so large that light takes 10 billion years to traverse it. Think about that. Light is the fastest thing, Nothing travels faster than light, and it takes light 10 billion years to go from one end of this structure to the other. Let that sink in. Let that really settle in your mind. We've only known about it for the last couple of decades because we only recently had telescopes good enough to map out the distances to galaxies over that vast a region, which means there could be other structures just as big or bigger that we haven't discovered yet because we haven't looked far enough, or our telescopes aren't good enough yet, or we don't know to look in those directions. We might be completely missing entire cosmic structures because we haven't looked far enough. The universe is constantly surprising us with its size and scale. Just when we think we've mapped it out, we find something bigger. Just when we think we understand it, we discover that we've only seen a tiny fraction. There's also the Sloan Great Wall, which is another huge structure, extending for over 1.3 billion light years. And the South Pole Wall, which was discovered relatively recently in 2020 and is absolutely massive, even bigger than the Sloan Great Wall, extending for about 1.4 billion light years. These walls of galaxies, these cosmic structures so large we can barely comprehend them. For a long time, people thought we had mapped most of the large-scale structure of the universe, but we keep finding bigger walls and filaments. It's humbling, honestly. We're like explorers who thought we had mapped most of the world, and then we kept finding new continents. Except these continents are made of galaxies and extend for billions of light years. One more wild thing to consider. The structures we're seeing right now are ancient. When we look at distant galaxies, we're looking back in time because light takes so long to reach us. So the cosmic web we're mapping isn't what the universe looks like now. It's what it looked like billions of years ago. The actual universe has been evolving since then. Structures have changed, galaxies have merged, the web has continued to develop. We're seeing a snapshot of the past and trying to extrapolate what the present looks like. It's like if archaeologists could only see ruins from 1,000 years ago and had to guess what modern cities look like. Except in this case, we're trying to see the present universe by looking at its fossil record written in light years. And the future. The universe is still expanding, and that expansion is accelerating due to dark energy. Eventually, billions of years from now, the universe will expand so much that all the structures we see now will be separated by such vast distances that they can't interact anymore. Galaxies will be isolated, separated by stretches of space so big that light couldn't reach from one to another in the entire remaining age of the universe. The cosmic web will still be there, technically, but it'll be shattered, disconnected. And eventually, so much time will pass that stars will burn out, black holes will evaporate through Hawking radiation, the universe will reach a state of infinite dilution, and all these structures that took billions of years to form will have been unmade. Which sounds depressing, but it's also kind of beautiful. The structures of the universe are temporary. They emerged from quantum fluctuations in the early universe, got organized by gravity into galaxies and clusters, and the cosmic web persisted for a few billion years, and then got torn apart by the expansion of space itself. It's tragic. It's also beautiful. Right now, at this very moment, you are moving. Not just moving through space because Earth orbits the sun and the sun orbits the galaxy and the galaxy rotates. You're moving through the universe in a very specific direction, and at a very specific speed that nobody even knew about for most of human history. Your entire galaxy, the Milky Way, with its 100 billion to 2 trillion stars, is being pulled through space by something so massive, so enormous, that it's warping the fabric of the cosmos itself. Something so vast that it stretches for hundreds of millions of light years. Something that contains thousands of galaxy clusters and hundreds of thousands of galaxies. And we still don't fully understand what it is at the deepest level. We call it the Great Attractor. We know it's pulling us. We know it's pulling everything in our local region of the universe. We know it's calling us across the void toward a massive structure called the Virgo supercluster. But we're still figuring out exactly what's happening and why. And that mystery is what makes this fascinating. When you zoom out from your local region and keep zooming out, past stars, past galaxies, past galaxy clusters, you reach a scale so large that it almost doesn't make sense to talk about it. You reach the scale of superclusters. A supercluster is basically what you get when you take galaxy clusters. Remember those? Hundreds or thousands of galaxies bound together by gravity. And you find that they themselves are grouped together into even larger structures. Superclusters are the largest gravitationally bound structures in the universe, or at least the largest ones we know about. They're on scales of hundreds of millions of light years across. They contain thousands of galaxy clusters, which contain hundreds of thousands of galaxies, which contain hundreds of billions of stars each. The numbers are incomprehensible, and you live inside one. You live in the Virgo supercluster. It's not the largest supercluster. There are others bigger, but it's the one you belong to. It's the cosmic neighborhood you call home. And the more you understand about it, the more you realize how much it shapes everything about your existence, from the most local scales all the way out to cosmic destiny itself. The Virgo supercluster wasn't always called that. For a long time, people thought the Virgo cluster was just, well, a cluster. It was a massive group of galaxies about 65 million light years away. Easy to see from Earth with telescopes, and it seemed like an isolated structure. But in the 1950s and 1960s, astronomers started realizing that the Virgo cluster wasn't alone. There were other clusters around it. There was the local supercluster, they called it. Then, as observational techniques improved and as astronomers realized they were seeing the same large-scale structure appearing again and again, they renamed it the Virgo supercluster, after its largest, most prominent component. The name stuck, even though most of the supercluster isn't actually in the constellation Virgo. Names in astronomy are weird like that. The Virgo supercluster is roughly 110 million light years across. That's the distance light travels in 110 million years. To put that in perspective, 110 million years ago on Earth, dinosaurs were still alive. The Cretaceous period was going strong. Velociraptors and Triceratops roamed the planet, and that's how long light would take to traverse this cosmic structure. It's enormous beyond comprehension. And inside this supercluster are thousands of galaxy clusters containing hundreds of thousands of galaxies. The Virgo cluster itself, the centerpiece, has over 1,300 member galaxies. The Coma cluster, another major member, has thousands of galaxies. And there are countless smaller groups and clusters scattered throughout. What's wild is that our local group, the collection of about 80 galaxies including the Milky Way and Andromeda, is part of the Virgo supercluster. We're not in the center. We're not near the major clusters. We're on the periphery, relatively isolated in what's called the local void region. It's a region with fewer galaxies, a quieter neighborhood. And from our position here on the edge, we're being pulled inward toward the center, toward the massive concentration of galaxies in the Virgo direction. This pull is the great attractor. For decades, astronomers noticed something weird. Galaxies in our local region weren't just moving away from us as expected from cosmic expansion. They were moving in a specific direction toward the constellation Virgo. It was like there was something pulling us, something massive, something invisible, the great attractor. It wasn't until the 1980s and 1990s that astronomers really understood what was happening. The great attractor is probably the supercluster's gravitational center pulling on all the matter around it. Actually, it's more complicated than that. The great attractor isn't a single object or even a single structure. It's a region. It's probably a concentration of dark matter and galaxy clusters in the direction of Virgo. It might be the central region of the Virgo supercluster. It might be something else entirely. But what we know for sure is that the local flow of galaxies, our motion through space, is directed toward something in that direction. We're being pulled. The whole local region is being accelerated inward. Think about that for a moment. Right now, at this very second, you're moving through space at hundreds of kilometers per second, not just because Earth orbits the Sun and the Sun orbits the galaxy, but because your entire supercluster is in motion. You're being pulled toward something. You've been pulled your entire life. Your species has been pulled. Your planet has been pulled. And for most of human history, nobody even knew it was happening. We thought we were stationary. We thought we were the center of everything. And all along, we were being swept through space by gravitational currents on scales so large they're almost impossible to visualize. When astronomers first discovered the great attractor, they had no idea what it was. The region where the attraction seemed to be coming from was obscured by the Milky Way's dust and gas. It was hidden behind our own galaxy. We couldn't see it. We had to infer its existence from the motion of distant galaxies and galaxy clusters. We had to do the math and work backward, and the math said something massive was out there, pulling everything toward it. This reminds me of something that happened when I was in high school. I was in physics class and we were learning about forces and motion, and the teacher drew a diagram with an object on a surface and a force pulling it. But the force was represented by a dotted line because it was invisible. And the teacher said, "How do we know forces exist if we can't see them?" And I raised my hand and said, "We see the effect." The teacher smiled and said, "Exactly. That's how we know dark matter exists too. We see the effect on visible matter and we infer what's there. That's the great attractor. We can't see it. We can't observe it directly, but we can see the effects. We can see how galaxies move. We can measure their velocities and their positions and the way they're flowing through space. And when we do the math, when we add up all the mass we can see and try to explain the observed motion, there's not enough. There's something else there, something we can't see, but we know is affecting everything around it. The great attractor region is thought to be at a distance of about 150 to 250 million light years away. That's far beyond the Virgo cluster itself, which is only about 65 million light years away. The Virgo cluster is actually kind of a local structure compared to the Great Attractor. The Virgo cluster is our nearby massive concentration, but it's not the whole story. The Great Attractor is pulling on the Virgo cluster too. Everything is part of this flow. Everything is being moved by this immense gravitational force. And here's what really gets me. We're not just sitting here passively being pulled. We're not victims of gravity. We're part of the structure. Our local group is part of the Virgo supercluster. When we're pulled toward the Great Attractor, when our motion is influenced by this massive structure, we're essentially part of a gravitational dance on cosmic scales. We're participating in the dynamics of the supercluster. Our motion isn't separate from the supercluster's dynamics, it's part of them. The structure of the Virgo supercluster isn't random. Like all superclusters, it has a shape. It's not spherical, it's elongated. It has filaments and sheets of galaxy clusters connected by less dense regions. The Virgo supercluster is often described as having a flattened or sheet-like structure with a local group on the edge of this sheet. We're like a small town on the edge of a vast flat continent. The continent is the supercluster, and that continent is part of an even larger structure, the cosmic web that fills the entire observable universe. When you map out all the superclusters in the observable universe, you see that they're arranged in a pattern. They're organized into something called the cosmic web. There are filaments of superclusters stretching across billions of light years. There are knots where multiple filaments intersect, creating regions of enormous density. And there are voids, vast empty regions with almost no galaxies or superclusters at all. The Virgo supercluster is one supercluster among many, located on one of these filaments. But what's interesting is how we discovered our place in all this. For a long time, thousands of years actually, humans thought Earth was the center of the universe. Then Copernicus and Galileo showed us that Earth orbits the sun. That was humbling. Then we realized the sun is just one star among billions in the Milky Way. That was even more humbling. Then we realized the Milky Way is just one galaxy among billions. That was humbling to the point of existential crisis for some people. And then we kept zooming out and we realized our galaxy is part of a local group, which is part of a supercluster, which is part of the cosmic web, which might itself be just local within an even larger universe. Every time we zoom out, we become smaller. Every time we understand more, we realize how little we are. But here's the thing. With that humbling comes a kind of beauty. It's beautiful to be part of something so vast and so organized. It's beautiful to understand how all these scales fit together, how galaxies fit into clusters, clusters fit into superclusters, superclusters fit into the cosmic web. There's an elegance to it. There's a structure that emerges from simple gravity acting over billions of years on the tiniest initial fluctuations. The Virgo supercluster probably formed the same way that all superclusters form. In the early universe, when there were tiny density fluctuations, regions slightly denser than average, gravity amplified those fluctuations. The dense regions attracted more matter. They got denser. They attracted even more matter. Eventually, after billions of years, you got the structures you see today. Galaxy clusters formed in the densest regions. The superclusters formed by grouping together the densest clusters. And it's still evolving. The Virgo supercluster isn't static. Galaxy clusters within it are merging. Galaxies are colliding, structures are changing. The supercluster is still settling under gravity, still organizing itself. In some sense, the universe at large scales is still young. The Virgo supercluster is still finding its final form. It will take many more billions of years to fully settle. One of the most fascinating things about the Virgo supercluster is that our understanding of it is still evolving. In 2014, astronomers identified a much larger structure containing the Virgo supercluster. They called it the Laniakea supercluster, using Hawaiian terminology meaning immense heaven. The Laniakea supercluster is about 520 million light-years across. It's enormous, and the Virgo supercluster is just one supercluster within it. This discovery completely changed how we think about our place in the universe. We thought the Virgo supercluster was our supercluster. We thought we lived on the edge of the main structure, but actually, we're on the edge of the Laniakea supercluster, and the Virgo supercluster is just part of that. This is how science works. We develop a model, we observe the universe, we refine our model. We think we understand our place, and then we zoom out a little further and realize we don't. There are probably even larger structures we haven't discovered yet. There might be structures so large they dwarf the Laniakea supercluster, the way the Laniakea supercluster dwarfs individual galaxy clusters. But let's get back to the Virgo supercluster specifically, because there's so much to unpack about it. The supercluster is home to numerous famous galaxy clusters, not just Virgo and Coma. There's the Fornax cluster, the Hercules cluster, the Leo cluster. There's our local group on the edge. There are countless smaller groups and associations. All of these structures are gravitationally bound together at the supercluster level. They're moving together. They're influencing each other through gravity. The Virgo cluster itself is fascinating. It's one of the nearest superclusters to us, which is why we can observe it so well. It's relatively close at 65 million light-years away. Within the Virgo cluster are some of the largest galaxies known. M87 is a giant elliptical galaxy that probably formed from the collision and merger of many smaller galaxies. It's a true cosmic monster containing trillions of stars. At its center is a supermassive black hole with a mass of billions of solar masses. We actually photographed the shadow of this black hole in 2019. It was the first image of a black hole ever directly captured. That image was taken at the Event Horizon Telescope, and it showed the shadow of M87's central black hole. The shadow was about 40 billion kilometers across. Think about that. The region of space-time that's so warped by the black hole's gravity that not even light can escape. That region is about 3 times bigger than the entire orbit of Earth around the Sun. Another giant galaxy in the Virgo cluster is M49, another giant elliptical. M87 and M49 are probably competing for dominance in the cluster. They're both massive. They're both pulling galaxies toward them through their gravity. The supercluster's structure is shaped by these massive structures pulling on everything else. The Virgo supercluster is also a place where we see lots of galactic mergers and interactions. Galaxy clusters are dense regions where galaxies bump into each other. Well, not literally bump, but come close enough that gravitational interactions affect them. When galaxies pass each other, their shapes get distorted. Sometimes they collide completely and merge. We see evidence of this throughout the Virgo supercluster. Irregular galaxies that have been mangled by close encounters, starburst galaxies with intense star formation triggered by collisions, galaxies in various stages of interaction, and our local group is being pulled into this environment. Right now, we're on the periphery, relatively isolated. The Virgo cluster is already pulling us. In billions of years, our local group, after Andromeda and the Milky Way merge, will have drifted closer to the Virgo cluster. Eventually, we might get pulled into it completely. We might merge with it. Our merged galaxy would join the cosmic dance of galaxies in the Virgo cluster. We'd be part of that dynamical environment. It's hard to imagine, but it's what's happening. Gravity is slowly pulling us inward. What fascinates me about all this is the scale of time involved. Cosmic processes work on timescales we can barely comprehend. We're talking about billions of years. The merging of the local group with the Virgo cluster might take billions of years. It's so slow that galaxies drift toward their destination at speeds of just hundreds of kilometers per second, fast in human terms, but glacially slow in cosmic terms. You could never see this happen. No individual would ever observe the motion. But it's happening. It's real. It's as inevitable as gravity itself. I remember watching a documentary once about the future of the universe. They were describing what would happen billions of years from now. They showed animations of the local group being pulled into the Virgo cluster, of galaxies merging, of structures evolving. And the narrator was talking about it in this calm, matter-of-fact way. But I was thinking, billions of years from now, if humans are still around, if civilization has lasted that long, if there are still beings looking up at the night sky trying to understand their place in the universe, their night sky will look completely different from ours. The familiar constellations will have changed. Andromeda will have merged with the Milky Way. New structures will have formed. The universe will have evolved, and they'll be looking up at a different cosmos than the one we see. That's one of the things that gets me thinking about cosmology. It's not just about understanding the universe as it is now. It's about understanding its history and its future. It's about understanding that you're living in a particular moment in cosmic time. The structures you see now, the galaxy clusters, the superclusters, they're temporary. They'll change. They'll evolve. They'll eventually be torn apart by the expansion of space if the current cosmological model's correct. Because here's the thing, the Virgo supercluster, like all superclusters, is embedded in the expanding universe. Space itself is expanding. Galaxies are being carried apart by this expansion. The farther away a galaxy is, the faster it's moving away from us, and the expansion is accelerating due to dark energy. This acceleration means that eventually, the Virgo supercluster will be so expanded that it will come apart. The structures that took billions of years to form through gravity will be torn apart by the expansion of space, but not yet. Right now, gravity still dominates at the supercluster scale. The Virgo supercluster is held together by its own self-gravity. The great attractor is pulling on local structures. The local group is being drawn inward. But billions of years from now, if dark energy continues to accelerate the expansion, the supercluster will eventually disconnect from the cosmic web. It will eventually be torn apart. The galaxies will be so far apart that none of them can interact anymore. This is called the heat death or big rip scenario, depending on the exact properties of dark energy. In the heat death scenario, The universe expands forever, getting colder and emptier, until eventually there's nothing left but cold darkness and isolated particles. In the Big Rip scenario, the expansion accelerates so much that it literally tears apart every structure, even atoms. We don't know which scenario is correct. We don't know enough about dark energy to be sure. But either way, the Virgo supercluster, this massive structure that's pulled on our galaxy and shaped our cosmic neighborhood, will not last forever. That's a sobering thought. It's a reminder that even the largest structures we know of are temporary. Even superclusters are temporary. In the far distant future, they'll be gone. The universe will be a different place, and so far as we can tell, there's nothing we can do about it. It's all determined by the laws of physics and the initial conditions of the universe. But right now, in this moment, the Virgo supercluster exists. It's massive, it's complex, it's beautiful, it's pulling us inward, and we're part of it. We're embedded in its structure. Our position in the universe, our location on the edge of the local group within the Virgo supercluster, part of the Laniakea supercluster embedded in the cosmic web, that's our cosmic address. That's where we are. Now let me tell you how we actually discovered the Great Attractor, because it's a pretty wild story of scientific detective work and careful observation. For decades, astronomers had been measuring the velocities of nearby galaxies using the Doppler effect. They'd measure redshifts. They'd calculate distances using Hubble's constant. They'd map out the motions of galaxies. And something strange kept showing up in the data. Galaxies weren't just moving away from us at speeds proportional to their distance, like Hubble's law predicted for a uniformly expanding universe. There was extra motion, a bulk flow, a coordinated movement of galaxies in a particular direction. It was like the local group of galaxies was being carried along by an invisible current, as if something was pulling us. In the 1980s, a team of astronomers led by Alan Dressler started doing systematic surveys of galaxy velocities. They measured the redshifts of hundreds of galaxies. They calculated their distances. They mapped out the velocity field, how fast and in what direction galaxies were moving. And they found something incredible. There was a huge flow of galaxies toward the constellation Virgo, a bulk motion toward one particular region of space. This was shocking because it didn't make sense according to the standard model. If the universe was expanding uniformly, galaxies should recede from us in all directions proportionally to their distance. But instead, there was this peculiar motion, this bulk flow, this motion toward Virgo. At first, they thought maybe it was the Virgo cluster doing the pulling. The Virgo cluster is massive after all, over 1,300 galaxies. It's one of the nearest superclusters to us, only 65 million light-years away. Maybe its gravity was just pulling on us. But when they did the math, it didn't add up. There wasn't enough mass in the Virgo cluster to explain the observed flow. So they looked further. They looked deeper into space, in the direction of Virgo. They tried to figure out what could possibly be massive enough to explain this huge bulk flow of galaxies. And they found hints of structure even farther away. They found evidence of more galaxy clusters in that direction. They found hints of something even bigger than the Virgo cluster itself, something that was even more distant, but even more massive. That something is what they called the Great Attractor. A massive concentration of matter somewhere in the direction of Virgo, probably somewhere between 150 and 250 million light years away. It's not a single object. It's probably not a single massive galaxy. It's probably a concentration of galaxy clusters, a region of particularly high density within the cosmic structure. It's probably part of the core region of the Virgo supercluster itself. What's wild is that we can't see the great attractor directly. It's obscured by dust in the Milky Way's disk. When you look in the direction of Virgo from Earth, you're looking through a lot of dust and gas in our galaxy. It blocks the view. It's like trying to see across a city when there's thick fog everywhere. You can't see clearly. But astronomers have learned to work around this. They use infrared telescopes that can peer through dust. They use observations at other wavelengths. They use mathematical models to infer what's there based on the motion of distant galaxies. And what they've concluded is that the great attractor is real. It's a massive structure. It's pulling on our local region. We're being swept toward it. Our local group, the Virgo cluster, all the galaxy clusters in the local region, they're all being pulled by this immense gravitational force. But here's what's fascinating. The great attractor itself might be being pulled toward something even larger. There are hints of even bigger structures farther away. There's the Shapley supercluster, a massive supercluster about 650 million light-years away in a slightly different direction. There might be a greater attractor beyond the great attractor, a hierarchy of gravitational structures pulling on each other on ever larger scales. This is the cosmic dance. This is how the universe organizes itself. Gravity creates structure. Structure attracts more structure. Everything is interconnected on cosmic scales through gravity. Nothing is isolated. Everything is being pulled by something. And we're all participants in this grand cosmic choreography. I remember the first time I really understood this. I was reading about the bulk flow of galaxies, about the great attractor, about how our local region was being pulled through space, and I was trying to visualize it. I was trying to imagine what it would feel like to be swept along by such enormous forces, and I realized that I am being swept along, that we all are, right now, this very second. We're all moving through space at hundreds of kilometers per second, not because we chose to, but because gravity is pulling us. And that's when it hit me. We're not observers of the cosmic structure. We're participants in it. We're not separate from the flow. We're part of it. We're being carried along like leaves in a river. Except the river is made of gravity and galaxy clusters, and it stretches across millions of light years. And that brings up a question that philosophers and scientists have been asking for centuries. Does our location matter? Does it matter that we're on the edge of a supercluster rather than in the center? Does it matter that we're part of a cosmic structure that's billions of light years across? Does it matter that we're being pulled toward something we can't even see? I think it does. I think our location shapes our perspective. It shapes what we can see. It shapes what we understand about the universe. It shapes what's possible for us. From our perspective here on the edge of the Virgo supercluster, we can see outward into the cosmic web. We can see other superclusters. We can measure the structure of the universe. We can observe the flow of galaxies. We can understand how we fit into it. If we were in the dense center of a supercluster, surrounded by countless galaxies packed so close together that we couldn't see beyond them. We might not be able to see out to the larger structures. We might think the supercluster was the whole universe. We might think we were at the center of everything. But from here, on the edge, in what's called the local void, a relatively quiet region with fewer galaxies than average, we can see far. We can understand the larger structure. We can see the filaments and walls of the cosmic web stretching across billions of light years. In that sense, our location is privileged, not in an egotistical way. We're not the center of anything. We're not the most important place in the universe. But in a practical sense, our position allows us to understand. It allows us to see the structure. It allows us to do cosmology. And that's valuable. That's why we can figure out that we're being pulled toward the great attractor. That's why we can map out the structure of the Virgo supercluster. We're positioned to observe it. And that observation changes everything about how we understand our place. Before we talk about other superclusters, let me tell you more about the internal structure of the Virgo supercluster, because it's actually really complex. It's not just a homogeneous blob of galaxies. It has structure within structure. There are dense regions and sparse regions. There are filaments and sheets of galaxy clusters. There are local voids, regions with fewer galaxies than average. The Virgo cluster itself is the most prominent feature. It's the gravitational center of gravity for the supercluster, or at least one of the major centers. But it's not the only major structure. There are other significant galaxy clusters scattered throughout. The Coma cluster, the Fornax cluster, the Eridanus group, the Leo group. Each of these is a gravitational structure with its own dynamics, its own galaxies, its own evolution. The Local group, our group containing the Milky Way and Andromeda, is actually one of the smaller structures within the supercluster. We're not particularly large. We're not particularly dense. We're on the periphery. We're in what's called the local void, a region of lower galaxy density. Around us are other groups in small clusters, but they're sparse enough that it's quiet, it's peaceful, it's isolated. But we're not completely isolated. We're connected to the rest of the supercluster through gravity. We're all part of one system. We're all influenced by the same gravitational forces. We're all participating in the same cosmic dynamics. The way astronomers study superclusters is really interesting. They can't just point a telescope at a supercluster and observe it directly. Superclusters are too large. They span hundreds of millions of light years. They're not discrete objects with clear boundaries. Instead, astronomers study them by surveying galaxies. They measure the redshifts of thousands or millions of galaxies. They calculate their distances using redshift and Hubble's constant. They map out the three-dimensional positions of galaxies in space, and then they look for large-scale patterns, regions of higher galaxy density, regions of lower density, streaming motions, bulk flows. This is how we discovered the great attractor. This is how we figured out that there's a bulk flow of galaxies toward Virgo. This is how we mapped out the structure of the Virgo supercluster. By painstakingly measuring the positions and velocities of galaxies one by one, building up a picture of the large-scale structure. Modern surveys like the Sloan Digital Sky Survey have mapped millions of galaxies. They've created three-dimensional maps of the cosmic structure. And from these maps, the large-scale structure becomes visible. The cosmic web reveals itself. The filaments of galaxy clusters emerge. The voids become apparent. It's like stepping back from a painting and suddenly seeing the big picture instead of just the individual brushstrokes. What's remarkable is how organized it all is. The superclusters aren't randomly scattered. They're arranged in an ordered pattern. They're organized into the cosmic web. They're part of a structure that extends across billions of light years. And that structure is still being discovered, still being mapped, still being understood. The Virgo supercluster is sometimes called the local supercluster because it's the one we live in. But as we've learned through decades of astronomical observation, there are other superclusters, many of them. The Coma supercluster, the Hercules supercluster, the Perseus-Pisces supercluster, the Bootes supercluster, the Shapley supercluster, the Pisces-Cetus supercluster, the Horologium supercluster. The universe is absolutely full of them. There are thousands of known superclusters, and there are probably many more that we haven't discovered yet. They're the basic building blocks of large-scale cosmic structure. They're what you get when you zoom out far enough and look at how galaxies are organized on the very largest scales. And the more we study them, the more we realize how much they teach us about how the universe organizes itself through the simple force of gravity. But here's where things get really mind-bending. The Virgo supercluster isn't the largest structure in the universe. It's not even close. In 2014, astronomers led by Brent Tully from the University of Hawaii made a discovery that completely changed how we think about our cosmic neighborhood. They mapped out what they called the Laniakea supercluster, a Hawaiian term meaning immense heaven, and they discovered that the Virgo supercluster is just one component of Laniakea. Laniakea is about 520 million light-years across. It contains about 100,000 galaxies. It dwarfs the Virgo supercluster. This was shocking to the astronomy community. We thought we knew our place. We thought we lived in the Virgo supercluster, our local supercluster. But actually, we live in the Laniakea supercluster, and Virgo is just a part of it. This is the third time in human history that we've had to revise our understanding of our cosmic address. First, we realized Earth orbits the Sun, not the other way around. Then we realized our Sun is just one star among billions in a galaxy. Then we realized our galaxy is just one among billions. Then we realized we're part of a supercluster. And now we've realized we're part of an even larger supercluster. Every time we zoom out, we become smaller. Every time we understand more, we realize how little we are. It's humbling. It's beautiful. It's the kind of realization that should make you think about what it means to exist in such a vast universe. The Laniakea supercluster contains multiple major superclusters, including Virgo and several others. The Perseus-Pisces supercluster is part of Laniakea. The Centaurus supercluster is part of Laniakea. The Pavo-Indus supercluster is part of Laniakea. And there are many smaller groups and clusters scattered throughout as well. It's a massive hierarchical structure, galaxy clusters within superclusters within superclusters of superclusters. The way Tully's team discovered Laniakea was by mapping the motion of galaxies on large scales. They noticed that galaxies within a certain region were all flowing toward a common center of mass. They were all being pulled by gravity. And when they calculated where that center of mass was and how large the structure had to be to explain the observed motions, they found that it was much, much larger than the Virgo supercluster alone. They found that the great attractor itself is inside Laniakea, not separate from it. The pull we feel toward Virgo is actually part of a larger flow toward the center of mass of Laniakea. This is the power of measuring motions in space. You can't see large structures directly, they're too big, they blend into the cosmic background. But you can measure how matter is moving. You can see the flow. You can infer the structure from the motion. And here's what's crazy. Laniakea itself might not be the largest structure. There are hints of even larger structures. The Shapley supercluster is enormous. There might be hyperclusters or superclusters, structures that contain multiple superclusters of superclusters. The hierarchy might go on even further than we can currently measure. We might be embedded in structures so large that we can't even perceive them yet. We might be participants in cosmic currents on scales so vast that they're beyond our current observational abilities. Every time we push the boundaries of what we can observe, every time we improve our instruments and our techniques, we discover that the universe is even larger and more organized than we thought. We discover new levels of hierarchy. We discover that we're embedded in larger and larger structures, so our cosmic address is really more complex than we usually think. We live in a solar system orbiting within a galaxy called the Milky Way, which is part of a galaxy group called the Local Group, which is part of a supercluster called the Virgo supercluster, which is part of a supercluster called the Laniakea supercluster, which is part of the cosmic web, which might be part of even larger structures we haven't discovered yet. It's structures all the way up. It's hierarchies within hierarchies, and at every level, gravity is the organizing force. Gravity pulls galaxies together into groups. Groups are pulled together into clusters. Clusters are pulled together into superclusters. Superclusters are pulled together into larger structures. It's gravity all the way down and all the way up. Before we go too deep into the philosophy, let me talk about what's going to happen to the Virgo supercluster in the future. Because that's actually pretty important for understanding our cosmic destiny. Right now, the Virgo supercluster is a gravitationally bound structure. The gravity holding it together is stronger than the expansion of the universe trying to pull it apart, so it persists. It remains organized, it maintains its structure, but that's not going to last forever. We know that dark energy is accelerating the expansion of the universe. We know that the expansion rate is speeding up. Eventually, and we're talking about many billions of years from now, the expansion will become so strong that it will overcome gravity at larger and larger scales. Eventually, it will overcome gravity even at the supercluster scale. But before we talk about the future, let me explain how the Virgo supercluster actually formed in the first place, because it's actually a pretty incredible story involving some mind-bending physics. The supercluster formed the same way that galaxies and galaxy clusters form, through gravity amplifying tiny initial density fluctuations over billions of years. In the early universe, right after the Big Bang, space was incredibly hot and dense. As it expanded and cooled, quantum fluctuations created tiny variations in density. Some regions were slightly denser than average. Some regions were slightly less dense. These variations were incredibly small at first, differences of 0.001% or smaller. But over time, gravity amplified them. Regions that were denser than average attracted more matter through their gravity. They became even denser. They attracted even more matter. It was a runaway process. Over billions of years, these tiny initial fluctuations grew into massive structures. The smallest fluctuations grew into galaxies. Larger fluctuations grew into galaxy clusters. Even larger fluctuations grew into superclusters. The Virgo supercluster formed from one of these large-scale density fluctuations. It took billions of years for gravity to organize the matter into the structure we see today. But it happened. It's still happening in a sense. The supercluster is still evolving. It's still settling under gravity. What's fascinating is that the structure of the supercluster reflects the structure of the initial density fluctuation. If the initial fluctuation was elongated, the supercluster is elongated. If the initial fluctuation had a particular pattern, the supercluster has that pattern. The initial conditions of the universe are imprinted on the structure we see today. The universe is like a fingerprint of its own past. The Virgo supercluster is thought to have formed from a particularly large density fluctuation. That's why it's so massive. That's why it contains so many galaxy clusters and galaxies. That's why it's one of the dominant structures in the local universe. And the initial density fluctuation was large, so the resulting supercluster is large. And the matter within the supercluster is organized in a particular way. There are dense regions, galaxy clusters like the Virgo cluster and the Coma cluster. There are less dense regions, the local void where our local group sits. There are filaments, thin, elongated structures of galaxy clusters and groups connected together. There are sheets, flattened structures of matter. It's all organized by gravity into this complex hierarchical structure. But what's important to understand is that all this structure is dynamic. It's not static. Things are moving, galaxies are flowing, matter is streaming. The local group is being pulled toward the Virgo cluster by its gravity. The Virgo cluster is being pulled toward the great attractor. Smaller structures are being pulled into larger structures. Matter is concentrating in some regions and being depleted from others. It's a cosmic dance that's been going on for billions of years and will continue for billions more. The flow of matter in superclusters is one of the most fascinating aspects of large-scale cosmology. Astronomers can measure this flow by observing the velocities of galaxies. They can see how galaxies are being pulled by gravity toward dense regions. They can see the convergence flows, matter moving toward galaxy clusters. They can see the divergence flows, matter being depleted from regions between clusters. It's like watching an enormous organism breathe, with matter flowing in and out, concentrating and dispersing. And we're part of this flow. Our local group is part of it. We're being pulled inward toward the denser regions. We're being organized by the same gravitational forces that organize all matter in the supercluster. We're participants in the cosmic dance. What this means is that the Virgo supercluster will eventually be torn apart, not immediately, not in the next few billion years, but eventually. The expansion of space, driven by dark energy, will become so strong that it will overcome gravity at larger and larger scales. Eventually, it will overcome gravity even at the supercluster scale. The expansion will pull galaxy clusters farther and farther apart. They'll become so separated that they can no longer interact gravitationally. The supercluster will disconnect from the cosmic web. It will be isolated. It will fragment. This is the ultimate fate of all superclusters, assuming our current understanding of dark energy is correct. This is what happens to all structure on the largest scales. Everything gets torn apart by the expansion of the universe. Everything becomes isolated. Eventually, even galaxies will be so far apart that none of them can interact. Each one will be alone in the darkness, a private universe unto itself. That's a sobering thought. It's a reminder that even the largest structures we know of, structures that span hundreds of millions of light years, structures that took billions of years to form, are temporary. They're not permanent. They're not eternal. They'll eventually be torn apart. They'll eventually cease to exist as coherent structures. But that's in the far, far future. For now, for the next many billions of years, the Virgo supercluster will continue to exist. It will continue to evolve. It will continue to pull on us. The local group will continue to drift inward. Eventually, we'll be pulled into the Virgo cluster. Our local group, after the Andromeda Milky Way merger, after billions of years of gravitational interactions, will join the cosmic dance of the Virgo cluster. We'll be part of that environment. We'll experience close encounters with other galaxies. We'll feel the effects of the cluster's dynamics. We'll be incorporated into something larger. And then, billions of years after that, the Virgo supercluster will be torn apart. Our galaxy, part of the merged local group, will be separated from the rest of the supercluster. It will be alone. It will be drifting through empty space with no neighbors, no companions, no other galaxies within reach. That's the future that awaits us. That's the cosmic destiny written by physics and dark energy. It's not cheerful, but it's the reality. It's the truth about what the universe will become. But here's the thing. It doesn't diminish the beauty of what we have now. It doesn't diminish the wonder of understanding how the universe is structured. It doesn't diminish the awe we feel when we contemplate the vast scales of cosmic structures. If anything, knowing that these structures are temporary makes them more precious. They exist for a time. They organize themselves through gravity. They persist for billions of years. And then they fade away. That's beautiful. That's profound. That's the kind of reality that should make us pause and think about our place in all this. The Virgo supercluster is a remarkable laboratory for studying how the universe organizes itself. It's close enough that we can observe it in detail. It's large enough that it contains all the major types of cosmic structures. It's structured in ways that teach us about fundamental physics and cosmology. When we study the Virgo supercluster, we're studying not just one local structure, but the mechanisms by which the entire universe organizes itself. The supercluster contains member clusters and groups in various stages of evolution. The Virgo cluster itself is probably in its prime, a massive mature structure that's already undergone multiple mergers and consolidations. The Coma cluster is similarly mature. But other smaller groups are less evolved. Some are just groups of a handful of galaxies that might someday merge with larger structures. Some are isolated groups that might remain relatively isolated for billions of years. This diversity makes the Virgo supercluster a perfect place to study galactic evolution. We can see galaxies in various stages of interaction. We can see the consequences of mergers, elliptical galaxies formed from the collision of spiral galaxies. We can see starburst galaxies with intense star formation triggered by gravitational interactions. We can see isolated spiral galaxies that have maintained their structure. We can see disturbed galaxies caught in the throes of close encounters. It's like a natural museum of galactic morphologies and interactions, and we can trace how things will evolve in the future. When we see two galaxies about to collide, we know what's going to happen. We've seen it happen in other places. We understand the physics. We can predict the outcome. When we see a small group being pulled toward a larger cluster, we know eventually it will be incorporated. We know it will lose its identity. We know its galaxies will be assimilated into the larger structure. So in studying the Virgo supercluster, we're studying not just its current state, but its past and its future. We're reading the history of cosmic evolution. We're seeing how structures form, evolve, interact, and eventually die. We're understanding the full life cycle of cosmic structures, and it all comes down to gravity. Every structure, every interaction, every merger, every evolution, it's all driven by gravity. Gravity is the sculptor of the cosmos. It's the force that shapes everything from planets to galaxies to superclusters. And understanding gravity is the key to understanding everything about how the universe works. I think that's what gets me most fascinated about studying superclusters like Virgo. It's not just the scale that's mind-bending, though that's impressive. It's the realization that everything, all this structure, all this organization, all this beauty, emerges from one simple force: gravity. Gravity pulling on matter, gravity organizing chaos into structure, gravity sculpting the cosmos. And we're part of it. We're embedded in it. Our existence depends on these gravitational structures. The Earth exists because gravity organized dust and gas around the sun. The sun exists because gravity organized gas into a star. The galaxy exists because gravity organized stars into a galaxy. The supercluster exists because gravity organized galaxies into a supercluster. We're nested within gravitational structures all the way down. When I was younger and first learning about gravity, I thought of it as a weak force. It seemed like the weakest of the fundamental forces. But as I've learned more about cosmology, I've come to understand that gravity is actually the most powerful force in the universe on large scales. Sure, the strong nuclear force and the electromagnetic force are stronger at small scales. But on cosmic scales, gravity dominates. Gravity shapes everything. Gravity is what makes the universe the way it is. That's humbling. That's profound. That's the kind of realization that changes how you see the world. Before we wrap up, I want to talk about why superclusters like the Virgo matter for modern cosmology. They're not just interesting as curiosities about our local cosmic neighborhood. They're crucial for testing our theories about how the universe works. They're essential for understanding cosmology itself. See, when cosmologists build models of the universe, they make assumptions about how matter is distributed. They assume the universe is roughly uniform on the largest scales, that if you zoom out far enough, every region looks about the same as every other region. This is called the cosmological principle. It's a fundamental assumption of modern cosmology. And it's probably right. But superclusters exist at scales where we can actually test this assumption. We can measure the distribution of matter. We can see if it really is uniform on large scales, or if there are significant variations. The study of superclusters is also crucial for understanding the growth of structure in the universe. We have computer simulations that model how structure grew from the tiny quantum fluctuations in the early universe to the massive superclusters we see today. We can compare those simulations to observations of real superclusters. We can see if the simulations match reality. If they don't, we need to revise our models. If they do, we gain confidence that we're on the right track. Superclusters are also important for understanding dark matter and dark energy. Dark matter is what actually holds superclusters together. Without it, gravity alone wouldn't be strong enough. By studying the motions of galaxy clusters within superclusters, we can infer how much dark matter there is and where it's distributed. And by observing how superclusters are being affected by the expansion of the universe, we can learn about dark energy. We can measure how fast the expansion is accelerating. We can constrain the properties of dark energy. So superclusters aren't just interesting objects in their own right. They're tools for understanding fundamental cosmology. They're laboratories for testing our theories. They're the largest structures we can observe in detail, and they teach us profound things about how the universe works. The Virgo supercluster specifically is exceptionally valuable for all of this because it's relatively nearby. We can observe it with good detail. We can map out its structure. We can measure the motions of its galaxies. We can do detailed studies that would be impossible for more distant superclusters. So in studying Virgo, we're learning things that apply to superclusters throughout the universe. We're learning universal principles that govern how structure forms and evolves on cosmic scales. There's also something philosophically important about superclusters. They're the largest structures in which we can see coherence. They're the largest structures that are still gravitationally bound, still organized into recognizable patterns. Beyond them, at even larger scales, structure becomes more diffuse. The cosmic web becomes more apparent, but individual superclusters become less important. Individual superclusters are absorbed into the larger scale patterns of the cosmic web. But within superclusters, we see clear structure. We see galaxy clusters, groups, individual galaxies, stars, planets. We see a hierarchy of organization that we can comprehend. Superclusters are the largest scales at which structure is still coherent and comprehensible to us. And that's kind of the edge of our cosmic understanding. We can study superclusters in detail. We can understand how they form and evolve. We can predict their future. But beyond them, things become hazier. The cosmic web stretches beyond our current ability to map in detail. There might be larger structures that we haven't discovered yet. There might be patterns in organization on scales so large that we can't even perceive them yet. So the Virgo supercluster represents both an end and a beginning. It's the culmination of our understanding of cosmic structure at the supercluster scale. It's the largest local structure in which we have detailed knowledge. But it's also a window into larger mysteries. Understanding Virgo teaches us about the cosmic web. Understanding Virgo helps us understand our place in the universe. One of the most important things we've learned from studying superclusters is that the universe is structured at every scale. From the smallest things we can observe, subatomic particles, to the largest things we can observe, superclusters billions of light years across. There's structure, there's organization, there are patterns, and it's all governed by the same physical laws. Gravity rules at every scale. Gravity organizes everything from atoms to galaxies to superclusters. The same equations that describe how planets orbit stars also describe how galaxy clusters orbit within superclusters. It's beautiful in its simplicity. Gravity. That's all it takes. Gravity and time and the initial conditions of the universe. Everything else follows. That's beautiful. That's profound. That's the kind of realization that makes you think differently about your place in the universe. You're not just a person on a planet orbiting a star in a galaxy in a supercluster. You're a part of all of it. The matter that makes up your body was forged in stars. The atoms in your brain were created in the cores of stars billions of years ago. You're literally made of stardust. You're made of the same matter that makes up galaxies and superclusters. And that same matter, that same atoms, participates in the motion of the supercluster. When the Virgo supercluster is pulled by the great attractor, that includes you. Your motion through space isn't just your personal motion, it's the motion of your entire supercluster. You're being swept along by gravity acting on cosmic scales. You're part of a current flowing through the universe. That's one of the most mind-bending aspects of cosmology. Realizing that you're not separate from the cosmic structures. You're not an observer of them from outside. You're part of them. You're embedded in them. Your existence is inseparable from the structure and dynamics of the universe. That's profound. That's philosophical. That's the kind of realization that changes how you see yourself. And it's all because of gravity. Simple gravity. The force that holds you to the ground. The force that keeps planets in orbit. The force that structures galaxies and superclusters. The same force that shapes everything from the smallest scale to the largest. Gravity is elegant. Gravity is powerful. Gravity is what makes the universe the way it is. The Virgo supercluster is one example of this. It's a gravitational structure. It's bound together by gravity. It's shaped by gravity. It's evolving under the influence of gravity. And it's pulling us inward. We're part of it. We're part of the cosmic dance that's been choreographed by gravity over billions of years. I remember when I first really understood this, that the Virgo supercluster was pulling on us, on our local group, on our galaxy, on our solar system, on us as individuals. I was reading about bulk flows and peculiar velocities and the great attractor, and it struck me that I was moving through space at hundreds of kilometers per second due to forces acting on me from structures hundreds of millions of light years away. My motion wasn't just local. It wasn't just my personal momentum. It was determined by cosmic forces operating at inconceivable scales. That's when it really hit me. We're not independent observers of the universe. We're embedded in it. We're participants in its dynamics. And that realization changed how I see everything. When I look at the night sky now, I don't just see distant points of light. I see the evidence of massive structures pulling on us. I see the Virgo supercluster reaching across space, drawing us toward it. I see myself as part of a cosmic flow, as part of the universal dance choreographed by gravity. The Virgo supercluster is vast beyond comprehension. It spans 110 million light years. It contains thousands of galaxy clusters and hundreds of thousands of galaxies and incomprehensible numbers of stars and planets. But despite its vastness, it's just one supercluster among thousands. It's a small player in the cosmic web. And despite being so enormous that light takes millions of years to traverse it, it's a temporary structure. Eventually, it will be torn apart by the expansion of space. But for now, it exists. For now, it pulls on us. For now, we're part of its structure and dynamics. And that's something worth taking a moment to contemplate. We live in a structure so vast and so ancient and so complex that it defies human imagination. We live in a structure created by simple gravity acting over billions of years on the tiniest initial fluctuations. We live in the Virgo supercluster, part of the Laniakea supercluster, part of the cosmic web, part of the universe. That dance continues. It will continue for billions of years more. Eventually, it will change. Eventually, dark energy will tear it apart. The supercluster will fragment. The galaxies will be isolated. The structure will dissolve. But for now, it persists. For now, we're part of it. And that's something worth contemplating. That's something that should make us pause and think about the nature of existence and our place in the cosmos. When you're lying awake at night, unable to sleep, staring at the ceiling, thinking about your life and your place in the world, remember this. You're being pulled through space at hundreds of kilometers per second by the gravity of a structure so vast that light takes millions of years to cross it. You're part of something cosmic. You're part of something ancient. You're part of something beautiful. That's the Virgo supercluster. That's your cosmic home. Imagine space so empty that you could travel for billions of light years and encounter almost nothing. No galaxies, no stars, no planets, nothing. Just darkness and the slow expansion of space itself. That's not a hypothetical scenario. That's not science fiction. That's reality. That's what a cosmic void is. And there's one called Lowe's North 13788 that's so massive and so empty that it challenges our understanding of how the universe is organized. It's a region billions of light years across where matter is so sparse that if you stood on a planet in one of the few galaxies in this void, you might never know other galaxies even existed. You might live your entire existence believing you were alone in the universe. When we talk about the structure of the universe, we usually talk about galaxies and clusters and superclusters and the cosmic web. We talk about filaments, those thin threads of galaxy clusters connecting across billions of light years. We talk about the interconnected network of structure that fills the cosmos, but we don't usually talk about the spaces between. We don't usually talk about the voids, and that's a mistake, because the voids are just as important to understanding cosmic structure as the filaments are. In fact, you could argue that the voids are more important because they define where the filaments are. The filaments are the walls. The voids are the empty space inside. The voids are where emptiness itself becomes a feature of cosmic organization. The Lowe's North 13788 void is one of the largest known cosmic voids. It's enormous. It's not a small pocket of emptiness. It's not a minor gap in the cosmic web. It's a region billions of light years across containing almost no galaxies at all. It's so empty and so vast that it challenges our understanding of how matter is distributed in the universe. And when you realize that you could live your entire life in a void like this and never encounter another galaxy, when you realize how utterly alone you would be, you start to understand what it really means for the universe to be structured the way it is. But how do we even know about voids? How do we discover and map regions that are defined by their emptiness? That's where the story gets really interesting. That's where the detective work of cosmology comes in. For a long time, astronomers didn't really think about voids. They were focused on finding and studying galaxies and clusters. The voids were just the empty space between the interesting structures. The voids were where nothing happens. But over the last few decades, as astronomers have done more sophisticated surveys of the universe, and created better three-dimensional maps of galaxy distribution, they've come to realize that the voids are actually fundamental to understanding cosmic structure. The voids define the cosmic web just as much as the filaments do. The filaments are the structure. The voids are the anti-structure. Together, they create the cosmic foam that fills all of space. The discovery of voids was accidental in a sense. It wasn't that astronomers went looking for voids. Rather, when they started creating detailed maps of where galaxies actually are in space, when they measured the three-dimensional positions of thousands and then millions of galaxies, they noticed gaps. They noticed regions where galaxies became sparse. They noticed that matter seemed to be organized in a particular pattern, concentrated in some places, absent from others. The first systematic recognition that voids existed came in the 1980s. Astronomers like Margaret Geller and John Hucra at the Center for Astrophysics were doing surveys of galaxy redshifts. They were measuring the distances to thousands of galaxies by observing how much their light was redshifted. And when they plotted the positions of these galaxies in 3 dimensions, a startling pattern emerged. The galaxies weren't uniformly distributed. They clustered in filaments and sheets, and between these structures were vast empty regions with almost no galaxies. One of the first voids they identified was the Boötes void, located in the constellation Boötes. It was a region containing almost no galaxies across a volume hundreds of millions of light years across. The discovery was shocking. Nobody had expected the universe to have such large empty regions. It forced cosmologists to revise their models of cosmic structure formation. It showed that the universe was far more organized and structured than they had realized. After the Boötes void was discovered, astronomers started looking for other voids. They found them everywhere. The local void, the relatively empty region surrounding our own local group, the Capella void, the Coma void, the Sculptor void. As surveys improved, especially with the Sloan Digital Sky Survey starting in the late 1990s, astronomers could map larger and larger volumes of space with greater and greater precision. And with this improved mapping came the discovery of more and more voids, some of them enormous. Lows North, 13,788 was identified through the Lows survey, the low redshift portion of the Sloan Digital Sky Survey. Lows targeted galaxies with lower redshifts, meaning nearer to us in cosmic terms, typically within about 500 million light years. By mapping the distribution of these relatively nearby galaxies, astronomers could see the structure of the nearby universe in detail. And when they mapped out the LOWZ galaxies, they identified this void in the northern sky, a region so empty that it stood out even compared to other voids, a region so sparse that it made the astronomers who identified it pause and ask, how empty can space actually be? What's wild is that despite being called a void, the Lows North 13,788 void is not completely empty. It still contains some galaxies, but they're so spread out, so isolated, that the void earns its name. If you could somehow navigate to one of those galaxies, a journey that would take you billions of light years, and you looked around from that galaxy, you would see emptiness. You would see a few dim specks of light from other distant galaxies, but they would be billions of light years away. You would be isolated. You would be profoundly alone. For us, living in a dense region where galaxy clusters are common, where the universe is filled with structure and organization, that's hard to imagine. We're embedded in a filament. We're part of the cosmic web. We're surrounded by structure. We have neighbors relatively close by in cosmic terms. The Andromeda Galaxy is only 2.5 million light-years away. The Virgo cluster is 65 million light-years away. The Coma cluster is 320 million light-years away. We have neighbors. We have structure. But in a void, you wouldn't. In a void, you would be profoundly alone. What's fascinating about voids is that they're not static features. They're not just empty pockets that formed early in the universe and have remained unchanged. They're evolving structures. They're growing. They're expanding. The voids are actually growing faster than the cosmic web as a whole is expanding. The galaxies are concentrating in the filaments, leaving more and more empty space in the voids. It's as if the universe is slowly segregating, matter clustering in filaments, emptiness growing in voids. This is a process that's been happening for billions of years and will continue for billions more. This happens because of how gravity works on large scales. In regions where there are more galaxies, gravity is stronger. Galaxies are attracted to each other, pulled by each other's gravity. So matter accumulates in these regions, the filaments become denser, the walls become more prominent. But in regions where there are fewer galaxies, the voids, gravity is weaker, there's less to pull on, so matter doesn't accumulate. In fact, galaxies in the voids might slowly drift away, pulled by gravity toward the nearby filaments. Over time, the voids empty out. The filaments become denser. The segregation increases. This is called the growth of structure in cosmology, and it's one of the most important processes in cosmic evolution. Early in the universe, the distribution of matter was relatively uniform, but tiny density fluctuations, regions slightly denser than average, grew over time due to gravity. The dense regions attracted more matter and became denser still. The sparse regions lost matter as it was pulled toward the dense regions. Over billions of years, this process created the filaments and voids we see today. The Lows North 13,788 void is probably at an advanced stage of this process. It's huge and nearly empty, which suggests it's been evolving for a very long time. The galaxies that were once in the void have been pulled out by gravity toward the surrounding filaments. What remains is an essentially empty region with just a few straggler galaxies that haven't yet been drawn away. These stragglers are like the last few customers at a store before it closes. They're there, but the process is essentially complete. When I first learned about cosmic voids, I had this weird reaction. Part of me found them fascinating. These enormous empty regions were like unexplored territories in the cosmic map. But another part of me found them kind of terrifying. The idea of being in a void, surrounded by billions of light years of emptiness, with no neighbors, no connection to the wider cosmic web, that's isolating. That's lonely on a scale that's hard to comprehend. It made me think about what it would be like to be an alien civilization living on a planet in one of those stray void galaxies. You would look up at the night sky. You would see a few distant stars from your own galaxy. You would see absolutely nothing else. You would have no idea that galaxies existed. You would have no idea that you were part of a universe teeming with billions of galaxies organized in a grand cosmic web. You would think you were the only galaxy in the cosmos. And then, if you developed advanced astronomy, If you pushed your telescopes to their limits, you might start to see hints of other galaxies at the very edge of your detection abilities. You might start to realize that the universe was larger and more populated than you thought. That would be an incredible discovery. That would be a moment that changed everything you understood about your place in the cosmos. And it would all be because you lived in a void. Your isolation would eventually lead to the greatest discovery of all. The way astronomers study voids is really interesting. They can't directly observe emptiness. They can't point a telescope at empty space and see anything. But they can map the distribution of galaxies. They can see where galaxies are and infer where they're not. They can create three-dimensional maps of galaxy positions across vast volumes of space, and when they do this, the voids become visible as regions of lower galaxy density. To map voids like LOWZ North 13788, astronomers measure redshifts. They take the light from galaxies, analyze its spectrum, measure how much the light is redshifted due to the universe's expansion, and calculate the distance. They do this for millions of galaxies. They plot their positions in 3 dimensions. And from that 3-dimensional map of galaxy positions, the structure of the universe emerges. The filaments become visible. The walls become visible. The voids become visible as conspicuous absences. The Low-Z survey was particularly good at mapping nearby galaxies. It identified about 40,000 galaxies with lower redshifts, meaning they're relatively close, within a few billion light years. That might sound like a huge distance, but in cosmological terms, it's nearby. It's the local universe. And by mapping these nearby galaxies in 3 dimensions, astronomers could see the local structure in detail. They could identify the filaments and walls and clusters and voids that define our local cosmic neighborhood. The discovery of voids was somewhat accidental in a historical sense. It wasn't that astronomers went looking for voids. Rather, when they started creating detailed maps of where galaxies actually are in space, when they measured the 3-dimensional positions of thousands and then millions of galaxies, they noticed gaps. They noticed regions where galaxies became sparse. They noticed that matter seemed to be organized in a particular pattern, concentrated in some places, absent from others. The first systematic recognition that voids existed came in the 1980s. Astronomers like Margaret Geller and John Huchra at the Center for Astrophysics were doing surveys of galaxy redshifts. They were measuring the distances to thousands of galaxies by observing their redshifts. And when they plotted the positions of these galaxies in 3 dimensions, a startling pattern emerged. The galaxies weren't uniformly distributed. They clustered in filaments and sheets, and between these structures were vast empty regions with almost no galaxies. One of the first voids they identified was the Boötes void, located in the constellation Boötes. It was a region containing almost no galaxies across a volume hundreds of millions of light years across. The discovery was shocking. Nobody had expected the universe to have such large, empty regions. It forced cosmologists to revise their models of cosmic structure formation. It showed that the universe was far more organized and structured than they had realized. After the Boötes void was discovered, astronomers started looking for other voids. They found them everywhere. The local void, the relatively empty region surrounding our own local group, the Capella void, the Coma void, the Sculptor void. As surveys improved, especially with the Sloan Digital Sky Survey starting in the late 1990s, astronomers could map larger and larger volumes of space with greater and greater precision. And with this improved mapping came the discovery of more and more voids, some of them enormous. Lows North. 13,788 was identified through the LOWS survey, the low redshift portion of the Sloan Digital Sky Survey. LOWS targeted galaxies with lower redshifts, meaning nearer to us in cosmic terms, typically within about 500 million light-years. By mapping the distribution of these relatively nearby galaxies, astronomers could see the structure of the nearby universe in detail. And when they mapped out the LOWZ galaxies, they identified this void in the northern sky. A region so empty that it stood out even compared to other voids. A region so sparse that it made the astronomers who identified it pause and ask, how empty can space actually be? What's wild is that despite being called a void, the LOWS North 13,788 void is not completely empty. It still contains some galaxies, but they're so spread out, so isolated, that the void earns its name. If you could somehow navigate to one of those galaxies, a journey that would take you billions of light years, and you looked around from that galaxy, you would see emptiness. You would see a few dim specks of light from other distant galaxies, but they would be billions of light years away. You would be isolated. You would be profoundly alone. For us, living in a dense region where galaxy clusters are common, where the universe is filled with structure and organization, that's hard to imagine. We're embedded in a filament. We're part of the cosmic web. We're surrounded by structure. We have neighbors relatively close by in cosmic terms. The Andromeda Galaxy is only 2.5 million light-years away. The Virgo cluster is 65 million light-years away. The Coma cluster is 320 million light-years away. We have neighbors. We have structure. But in a void, you wouldn't. In a void, you would be profoundly alone. But that also made me think about what voids tell us about the universe. They tell us that the universe isn't uniform. They tell us that matter is organized, that it clusters in some places and is sparse in others. They tell us that the cosmic web has structure and pattern. They tell us that emptiness is as much a part of cosmic structure as structure itself. The voids aren't random. They're not accidents. They're fundamental features of cosmic organization. The way astronomers study voids is really interesting. They can't directly observe emptiness. They can't point a telescope at empty space and see anything. But they can map the distribution of galaxies. They can see where galaxies are and infer where they're not. They can create three-dimensional maps of galaxy positions across vast volumes of space. And when they do this, the voids become visible as regions of lower galaxy density. To map voids like LOWZ North 13,788, astronomers measure redshifts. They take the light from galaxies, analyze its spectrum, measure how much the light is redshifted due to the universe's expansion, and calculate the distance. They do this for millions of galaxies. They plot their positions in 3 dimensions. And from that 3-dimensional map of galaxy positions, the structure of the universe emerges. The filaments become visible. The walls become visible. The voids become visible. The LOWS survey was particularly good at mapping nearby galaxies. It identified about 40,000 galaxies with redshifts below a certain threshold, which means they're relatively close. within a few billion light years. That might sound like a huge distance, but in cosmological terms, it's nearby. It's the local universe. And by mapping these nearby galaxies in 3 dimensions, astronomers could see the local structure in detail. They could identify the filaments and walls and clusters and voids that define our local cosmic neighborhood. One of the surprising discoveries from mapping the LO's galaxies was how large and how empty some voids were. LO's North, 13,788, emerged as one of the largest. It's a region spanning hundreds of millions of light years in which galaxies are separated by enormous distances. Astronomers can measure the distance between galaxies in the void. They can determine how sparse it really is. They can quantify the emptiness, and when they do, they find that LOWZ North 13,788 is genuinely, remarkably empty. If you were somehow in one of the galaxies in the LOW's North 13,788 void, even your nearest galactic neighbor would be tens of millions of light years away. You would be alone. You would see nothing but darkness around you. Even with advanced telescopes, even pushing the limits of detection, you would see very little. You would be isolated from the cosmic web. You would be alone in the darkness. This brings up a profound philosophical question. What is the nature of emptiness in the universe? Is emptiness real? Is it meaningful? In the void, emptiness isn't just the absence of structure. It's an actual feature of the cosmic architecture. The voids define the cosmic web just as much as the filaments do. You can't understand the filaments without understanding the voids. They're complementary. They define each other. The LOW's North 13788 void stretches across hundreds of millions of light years. Its exact size is hard to define because the boundaries are fuzzy. Astronomers typically define void boundaries based on some threshold, a particular density level below which they call it a void. But the exact size depends on the threshold you choose. Some definitions might make the void smaller. Others might make it larger. But regardless of the exact definition, LOW's North 13,788 is definitely one of the largest known voids. One of the surprising discoveries about voids is that they have structure themselves. You might think that a void would just be completely empty and featureless, but when astronomers map them out in detail, they find that voids have boundaries. The boundaries aren't sharp. They're not like a wall dividing the void from the surrounding filaments. But there is a transition region. There are walls of galaxies surrounding the voids, thin shells of matter that enclose the emptiness. These walls define the void. Without them, the void would just be part of the general sparse structure of the universe. The LOW's North 13788 void has these walls. It has a defined boundary, even if that boundary is somewhat fuzzy. The wall is like the skin of an enormous bubble, with the void filling the inside. The walls contain most of the galaxies, while the void itself is nearly empty. This structure, walls surrounding voids, is a fundamental feature of the cosmic web. The walls are the filaments and sheets where matter concentrates. The voids are the empty space between. Some voids have internal structure as well. They might have smaller void bubbles, like foam within foam. They might have elongated or irregular shapes rather than being perfectly round. They might have substructure that reflects how they formed and how they've evolved. The LOW's North 13788 void, despite being mostly empty, probably has some of this internal structure. It probably isn't a featureless sphere of emptiness. It probably has a shape that reflects its history and its physics. The study of voids has revolutionized how we think about large-scale structure. For decades, cosmologists focused on trying to understand how structure forms and grows. They built simulations of cosmic evolution. They predicted how matter should cluster under gravity. And their predictions worked pretty well for explaining the filaments and clusters in the general cosmic web. But the voids revealed something unexpected. The simulations didn't always predict voids that were quite as empty as the voids we observe. The simulations didn't always predict voids quite as large as what we see. This discrepancy forced cosmologists to refine their models. It showed that our understanding of how cosmic structure evolves was incomplete. It drove progress in cosmology. It pushed us to think more carefully about the physics of structure formation. It reminded us that even when we think we understand something, the universe has a way of surprising us and forcing us to revise our understanding. The Laos North 13788 void represents one of the largest, emptiest regions we've identified. Studying it helps us understand not just that particular void, but voids in general. It helps us understand how matter is distributed in the universe. It helps us understand cosmic structure and its evolution. What's remarkable about cosmic voids is how they highlight the difference between the universe we might expect and the universe that actually exists. If matter were distributed randomly, if there were no gravity organizing it, you would expect a fairly uniform distribution of galaxies. Galaxies would be scattered throughout space with roughly equal density everywhere. But gravity changes everything. Gravity creates structure. Gravity concentrates matter in some places and leaves voids in others. The Laos North 13788 void represents the endpoint of this gravitational organization. It's a region where gravity has been so effective at pulling matter away that almost nothing remains. It's a region where the process of structure formation has nearly reached completion. It's a region where isolation has become the dominant feature. It's a cosmic desert where the water of matter has been drawn away, leaving behind only a few oases of galaxies. This brings up an interesting philosophical point. The universe contains regions of profound emptiness. It contains places where loneliness is not a personal feeling, but a cosmic fact. It contains voids hundreds of millions of light years across with almost no galaxies at all. That's part of the cosmic reality. That's part of how the universe actually is. And when you understand that, when you really internalize it, you start to see the universe differently. You start to see the cosmic web not as a simple connected network, but as a complex interplay between structure and emptiness, between connection and isolation, between density and sparsity. You start to understand that the universe has organized itself into a delicate balance between these extremes. The filaments are the places of connection. The voids are the places of isolation. Together, they create the cosmic structure that we observe. In studying voids, astronomers are also studying what it means for structure to exist. What makes a structure real? Is it defined by what's there or by what's not there? In a void, the definition of the structure is almost entirely defined by the absence of matter. The void is a structure made of emptiness. That's philosophically interesting. That changes how we think about cosmic structure. The fact that we can identify and study voids like LOWZ North 13,788 is remarkable. Just a few decades ago, we didn't even know voids existed. Now we're mapping them, measuring them, understanding their properties. We're using them to test our theories about cosmic structure formation. We're using them to refine our understanding of how the universe has evolved. We're using them to understand fundamental truths about the cosmos. What's remarkable about voids is how they complement the filaments and sheets of the cosmic web. The filaments are places of high density, high activity, frequent galaxy interactions. They're where the cosmic drama happens. But the voids are the opposite. They're places of isolation, emptiness, quiet. They're like the space between the lines in a painting, the negative space that defines the positive space. And when you realize that the universe is made of both, that it has filaments and voids, that it has structure and emptiness, you start to understand that cosmic organization is more sophisticated than we usually give it credit for. It's not just about things clustering. It's about an organized interplay between density and sparsity, between structure and emptiness, between the populated filaments and the desolate voids. The Lows North 13,788 void stretches across hundreds of millions of light years. Its exact size is hard to define because the boundaries are fuzzy. Astronomers typically define void boundaries based on some threshold, a particular density level below which they call it a void. But the exact size depends on the threshold you choose. Some definitions might make the void smaller, others might make it larger. But regardless of the exact definition, the Lows North 13,788 void is definitely one of the largest known voids. It might contain only a few thousand galaxies across its entire volume. For comparison, a region of similar size in a dense part of the cosmic web might contain millions of galaxies. The difference is staggering. The contrast is profound. In the dense regions, galaxies are packed together, interacting frequently, merging, creating complex dynamics. In the voids, galaxies are isolated, separated by enormous distances, rarely or never interacting. This has profound implications for galaxy evolution. Galaxies in filaments have very different evolutionary histories than galaxies in voids. Galaxies in filaments experience frequent gravitational encounters with other galaxies. These encounters can trigger star formation. They can drive mergers. They can transform the structure and morphology of galaxies. But galaxies in voids don't experience these encounters. They evolve in isolation. They might maintain their structure for billions of years without significant disturbance. So if you somehow could compare a galaxy in the Lows North 13,788 void with a galaxy of similar initial properties in a dense filament, they would look very different today. The void galaxy would be pristine, undisturbed, maintaining its original structure. The filament galaxy would be transformed, altered by countless gravitational encounters and mergers. This difference is observable. Astronomers can study galaxies in voids and galaxies in filaments and see these differences directly. This is one reason why voids are scientifically interesting. They're like cosmic laboratories where you can study how galaxies evolve when they're isolated. They're natural experiments in which the variable of galactic interaction has been minimized. They let us understand what part of galaxy evolution is due to internal processes and what part is due to external interactions. The Lows North 13,788 void is one such laboratory. One of the most beautiful things about studying voids is that it reminds us how much we still don't know. We know the universe has voids. We know they're large and empty. We know they're important for understanding cosmic structure. We know they're growing over time. We know they have internal structure and defined walls. But we still have questions. How do voids evolve in detail? What determines their exact shape and size? How do they interact with the surrounding filaments? What happens at the boundaries? How do the walls form and evolve? These questions are still being investigated. This is active research. This is the frontier of cosmology. When you think about the Lowe's North, 13,788 void, when you try to imagine hundreds of millions of light years of emptiness, when you contemplate what it would be like to live in one of the few galaxies scattered throughout that vast void, you start to understand something profound about the universe. You start to understand that we're privileged in our location. We live in a dense region. We're surrounded by structure. We have neighbors. We can see the cosmic web. We can understand how the universe is organized. But somewhere out there are galaxies in the low Z North, 13,788 void, and other voids. There are observers in those distant void galaxies who might not even know that the cosmic web exists. They might not be able to see the filaments and walls and clusters that define cosmic structure. They might think they're isolated. They might think they're alone in an empty universe. And in a sense, they would be right. From their perspective, the universe would look very different from the universe we see. That's a sobering thought. It reminds us that our perspective is limited. It reminds us that the universe looks different from different places. It reminds us that the structure we see is a direct result of where we are within that structure. It reminds us to be humble about our understanding. We think we see the whole universe, but we're really seeing just one piece of it, the piece we live in. And that piece has its own particular characteristics shaped by voids and filaments and walls and sheets. But it also reminds us of something beautiful. It reminds us that the universe has organization on every scale. From galaxies to clusters to superclusters to the cosmic web itself, there's structure. From filaments to voids to walls to sheets, there's pattern. And understanding that pattern, mapping out that structure, exploring the frontiers of our knowledge, that's what drives cosmologists forward. That's what makes the study of the universe so compelling. That's why we care about the Lowe's North, 13,788 void. The Lowe's North, 13,788 void stretches across hundreds of millions of light years. Its exact size is hard to define because the boundaries are fuzzy. But it's definitely one of the largest known voids. It might contain only a few thousand galaxies across its entire volume. For comparison, a region of similar size in a dense part of the cosmic web might contain millions of galaxies. The difference is staggering. Galaxies in filaments have very different evolutionary histories than galaxies in voids. Galaxies in filaments experience frequent gravitational encounters with other galaxies. These encounters trigger star formation. They drive mergers. They transform the structure of galaxies. But galaxies in voids don't experience these encounters. They evolve in isolation. They might maintain their structure for billions of years without significant disturbance. If you compared a void galaxy with a filament galaxy of similar initial properties, they would look very different today. The void galaxy would be pristine, undisturbed. The filament galaxy would be transformed, altered by countless encounters and mergers. This difference is profound. You could tell which one lived in a void just by looking at it. This is why voids are scientifically interesting. They're cosmic laboratories where you can study isolated galaxy evolution. They're natural experiments. The Lowe's North 13,788 void is one such laboratory. Its galaxies are fossil records of undisturbed cosmic evolution. There's another fascinating aspect of voids. They expand faster than the universe as a whole. Voids have lower density. In low-density regions, the expansion of space isn't as much counteracted by gravity, so voids expand faster. This means over time, voids become even larger and more empty. It's self-reinforcing. Emptiness breeds more emptiness. This has implications for the far future. If dark energy continues accelerating expansion and galaxies continue drifting toward filaments, the universe might eventually consist of isolated dense filaments surrounded by enormous voids. The structure we see now might become even more pronounced. The segregation between density and emptiness might become extreme. The Lowe's North 13,788 void might grow even larger. It might become even more empty. In billions of years, if observers existed then, they might see a radically different cosmic web. They might see isolated filaments surrounded by enormous voids spanning billions of light years. They might see structure and emptiness separated on scales even larger than we observe now. The universe is evolving. The cosmic web is evolving. The Lowe's North 13,788 void is evolving. When I contemplate this void, when I try to imagine it, I think about the geometry of absence. I think about how absence itself has shape and structure. I think about how emptiness is organized. The void defines the filaments around it just as much as the filaments define the void. They're complementary. Filaments and voids exist together. You can't have one without the other. This is philosophically interesting. Structure is usually thought of as the arrangement of matter. But in a void, structure is defined by the arrangement of emptiness. The void is structured by what's not there. This suggests that structure is a more abstract concept than we usually treat it. Structure is about pattern and organization, whether in matter or emptiness. The Lowe's North 13788 void represents something profound about the universe. It represents the principle that things organize themselves into complementary forms. Density breeds emptiness. Emptiness follows density. Structure and its complement exist together. This principle appears throughout nature, positive and negative, light and dark. The universe organizes itself into complementary polarities. The Lowe's North 13,788 void is one manifestation of this principle. It's a region of emptiness that exists because of density elsewhere. It's a void that defines the filaments around it. It's part of a larger pattern that stretches across billions of light years. It's part of the cosmic dance that's been choreographed by gravity over billions of years. One of the most beautiful things about studying voids is that it reminds us how much we still don't know. We know voids exist. We know they're large and empty. We know they're important for cosmic structure. We know they're growing. We know they have internal structure and walls. We know they affect galaxy evolution. But we still have questions. How do they evolve in detail? What determines their shape and size? How do they interact with filaments? What happens at boundaries? These questions are still being investigated. This is active research. This is the frontier of cosmology. The Lowe's North 13,788 void represents a frontier. It represents a boundary of our knowledge. When we study it, when we map it, when we try to understand it, we're pushing the boundaries of what we know. We're exploring territory not yet fully understood. We're asking questions not yet fully answered. We're engaging with the cosmos at the frontiers of human knowledge. Astronomers continue to study this void. They continue to refine measurements. They continue to test models. The Lowe's North 13,788 void is not just empty space. It's a key to understanding the universe. It's a puzzle piece. It's a place where the universe reveals its secrets. When you're lying awake at night, unable to sleep, staring at the ceiling, thinking about your place in the world, remember this. There's a void billions of light years across with almost no galaxies in it. There are galaxies in that void isolated by billions of light years from any neighbors. There are observers in those galaxies, if they exist, who see a universe that looks nothing like ours. And all of that exists. All of that is real. All of that is part of the cosmic structure. We live in just one small part of an incomprehensibly vast and intricately organized universe. That thought changes something. That thought makes you realize how privileged we are to live where we do. That thought makes you realize how much universe there is beyond our immediate reach. That thought makes you humble.